Hello there and welcome back to the Science Sleepy Minds. Tonight, picture this. You're floating in absolute darkness, billions of miles from the nearest streetlight, the nearest campfire, the nearest anything. There is no sound out here, no wind against your cheek, no rustle of leaves. Just a cold so profound it makes Antarctic winters feel like a beach holiday. And somewhere in this impossibly vast nothing, a little spacecraft no bigger than a compact car is tumbling forward at 38,000 miles per hour, carrying a golden phonograph record etched with the sounds of Earth. Whale songs, Beethoven, a baby crying, Chuck Berry, the murmur of a human pulse. You probably would not survive more than about 15 seconds out here without a spacesuit. But that little machine has been thriving for nearly half a century, and tonight you are going to ride alongside it. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you are listening from and what time it is where you are. I always love reading those. Someone is always tuning in at 3 in the morning from somewhere unexpected. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You settle back against your pillow, and the story begins not in outer space, but on a very terrestrial afternoon in 1977. The air at Cape Canaveral smells of salt marshes and rocket fuel, which honestly is a combination no candle company has ever tried to market, and maybe for good reason. A Titan III E Centaur rocket stands on the pad, white vapour curling from its flanks like the breath of some hibernating dragon. Inside the payload fairing sits Voyager 2, which, in one of NASA's most delightfully confusing naming decisions, actually launches first. Voyager 1 will follow 16 days later on a faster trajectory, eventually overtaking its twin-like younger sibling sprinting past you on the stairs. But right now, in this humid Florida afternoon, Voyager 2 is the one trembling on the launch pad, and the engineers in the control room are quietly terrified. You would be terrified too if you had spent the better part of 5 years convincing Congress to fund a mission that depends on a planetary alignment so rare it happens only once every 176 years. Jupiter, Saturn, Uranus and Neptune are about to line up in a cosmic relay that allows a single spacecraft to hop from one giant planet to the next, borrowing a little gravitational energy at each stop like a traveller bumming rides across the countryside. Miss this window, and you wait until roughly the year 2153 for the next one. No pressure at all. The idea for this grand tour originated in the mid-1960s when a young aerospace engineer named Gary Flandreau at the Jet Propulsion Laboratory was plotting possible trajectories and realised the outer planets would soon be arranged in just the right way. Historians still argue whether Flandreau's original memo fully appreciated how transformative the mission would become, or whether he simply saw an elegant math problem begging to be solved. Either way, his calculations lit a slow fuse that would eventually carry 2 small robots to the edge of everything we call home. Now here's a quirky little detail that almost never makes it into the documentaries. The original mission concept was not called Voyager at all. It was called the Grand Tour, and it envisioned 4 or even 5 spacecraft fanning out across the outer solar system like seeds from a dandelion. Budget cuts, as usual, crushed that dream down to 2 spacecraft and a more modest title. The Voyager name was actually recycled from a cancelled Mars mission, a piece of bureaucratic thriftiness that somehow ended up branding the most far-reaching journey in human history. Imagine naming the greatest road trip ever taken after a rental car that somebody returned early. You feel your breathing slow a little as you picture those twin spacecraft taking shape in a clean room at JPL in Pasadena, California. Each one weighs about 800 kilograms, roughly the mass of a grand piano if you stuffed it with scientific instruments and bolted a large radio dish on top. The main antenna is 3.7 meters across, a wide white ear designed to whisper back to Earth. From distances no human-made object has ever attempted. Beneath it hang 10 science instruments, each one a miniature laboratory devoted to a different slice of reality. There are cameras for visible light, spectrometers for ultraviolet and infrared, magnetometers for sensing magnetic fields, and particle detectors for counting the tiny bullets of radiation that zip through space. There is even a device called the Plasma Science Experiment, which measures the soup of charged particles streaming outward from the Sun. That instrument, quiet and unassuming in 1977, will become the star witness decades later when Voyager finally reaches the edge of the solar system and needs to prove it has actually crossed the line. And then, of course, there is the golden record. You've probably seen pictures of it, a gold-plated copper disc tucked inside an aluminum jacket on the side of each spacecraft, complete with a stylus and pictographic instructions for any extraterrestrial civilization that might stumble upon it. The committee that chose its contents was chaired by Carl Sagan, who approached the task with the seriousness of someone curating humanity's greatest hits album for an audience that might not have ears. The record contains 116 images, greetings in 55 languages, 90 minutes of music ranging from Bach to Blind Willie Johnson, and a collection of natural sounds including thunder, birdsong and the rumble of a rocket launch. One member of the committee wanted to include the sound of a human kiss, which made it onto the record, and another suggested including a recording of brain waves, which also made it. The brain waves belong to Anne Druyan, who was in the early, secret stages of falling in love with Sagan at the time, a detail so sweetly human it almost makes you forget the terrifying emptiness these records are sailing into. You hear the countdown in your mind, feel the low rumble through the soles of your imaginary shoes. The Titan rocket ignites, and Voyager 2 climbs into a pale blue sky on August 20th, 1977. 16 days later, Voyager 1 follows. Within hours, both spacecraft are beyond the Moon's orbit, farther from home than any human has ever travelled, accelerating toward Jupiter with nothing but mathematics and three-body physics keeping them on course. The Deep Space Network, a trio of enormous radio dishes spaced around the globe in California, Spain, and Australia, locks onto their signals and begins a conversation that will last longer than most civilizations. You nestle deeper into your blankets. The rockets have finished their roaring. The spacecraft are coasting now, silent as two silver fish, gliding through a dark ocean, and everything ahead of them is discovery. The Cold War is a strange incubator for exploration, but you have to admit it is an effective one. You lie there in the dark and let your mind drift back to the late 1960s and early 1970s, a time when the United States and the Soviet Union were locked in a contest that turned rocket science from an academic curiosity into a national obsession. The Apollo program has just planted boots on the moon, and for a brief shimmering moment the American public believes that space is a place you can simply go, the way you might drive to the coast on a long weekend. NASA's budget, however, is already shrinking. Vietnam is expensive. Social programs are expensive. The idea of sending robots to the outer planets sounds, to many members of Congress, like buying a telescope when the roof is leaking. Yet the planets do not care about federal budgets. Jupiter, Saturn, Uranus and Neptune are drifting into the once-in-176-year alignment, and a small group of engineers at the Jet Propulsion Laboratory knows that if the window closes without a launch, everyone in the room will be long dead before the next one opens. You can almost feel the quiet desperation in those fluorescent-lit offices in Pasadena. Coffee cups multiplying on desks, trajectory plots pinned to corkboards like treasure maps. Gary Flandreau's original calculations from 1965 have been refined and re-refined, and by the early 1970s the math is undeniable. A spacecraft launched in the late summer of 1977 can use Jupiter's gravity to sling itself to Saturn, Saturn's gravity to sling itself to Uranus, and Uranus's gravity to fling it onto Neptune, each planet acting like a cosmic paddle in the universe's most elaborate game of ping-pong. Gravity assists are one of those concepts that sound almost like cheating, and honestly, they sort of are. You picture a ball rolling downhill toward a moving truck. If the ball bounces off the truck at just the right angle, it picks up some of the truck's momentum and flies away faster than it arrived. Replace the ball with a spacecraft and the truck with Jupiter, and you have the basic principle. The spacecraft does not actually touch the planet, of course. It swoops through the gravitational field, steals a tiny fraction of the planet's orbital energy, and accelerates onward. Jupiter, in return, slows down by an amount so infinitesimally small that you would need scientific notation with an embarrassing number of decimal places to even express it. The planet does not notice. You, riding along on the spacecraft, get a free speed boost worth thousands of miles per hour. It is the best deal in physics, and it is the only reason Voyager is possible on a budget that, adjusted for inflation, is roughly what a mid-sized city might spend on a new football stadium. Here is a mainstream historical fact that deserves a moment of appreciation. The entire Voyager program, both spacecraft, both launches, all the ground support and decades of mission operations, cost approximately $865 million at the time. That is less than the production budget of several modern Hollywood film franchises. You're essentially telling the universe your life story for the price of a few superhero sequels, which, depending on your opinion of superhero sequels, may or may not be a bargain. Now, the original Grand Tour concept, the one with 4 or 5 spacecraft visiting every outer planet, was estimated to cost considerably more, and that is where the political knife came down. NASA administrators, ever resourceful in the art of bureaucratic survival, repackaged the mission as a more modest 2 spacecraft flyby of Jupiter and Saturn only. The extended mission to Uranus and Neptune was written into the plan as a quiet possibility, the kind of stretch goal you mention in a footnote so that nobody can accuse you of over-promising. Scholars still debate whether this was genuine fiscal caution or a deliberate strategy to get the program approved, with the unspoken understanding that once the spacecraft were flying and returning spectacular data, Congress would find it politically impossible to pull the plug. If it was a bluff, it worked beautifully. You smile a little in the darkness, appreciating the hustle. Building the spacecraft themselves was its own odyssey. JPL had to design machines that could survive more than a decade in space, endure radiation fields around Jupiter that would fry most electronics, and operate autonomously for hours at a time because radio signals at those distances take so long to travel that real-time control is impossible. The engineers settled on a 3-axis stabilized design, meaning the spacecraft do not spin for stability the way earlier probes did. Instead, they use small thrusters and reaction wheels to hold themselves steady, always keeping that big dish antenna pointed back at Earth like a dog that refuses to stop staring at the door waiting for its owner. The brains of each Voyager are 3 interconnected computers, each one running on about 69 kilobytes of memory. To put that in perspective, a single photograph on your phone today contains more data than everything Voyager's computers can hold simultaneously. These machines were built with 1970s technology, which means they run on the kind of processing power that would struggle to operate a modern toaster. And yet they have been making autonomous decisions in deep space for nearly 50 years, which is more than you can say for most software updates. A quirky little detail that rarely gets mentioned is the matter of the backup spacecraft. NASA actually built a 3rd Voyager, or more precisely, a structural test model and spare parts assembly that could have been converted into a flight unit if one of the primary spacecraft had failed during testing. This backup never flew, and parts of it were eventually cannibalized for other projects. Somewhere in the storage rooms of JPL, pieces of what might have been Voyager 3 sit quietly gathering dust, a ghost sibling that never got to leave home. Power for each spacecraft comes from 3 radioisotope thermoelectric generators, those dark cylindrical objects jutting out on booms behind the main body. Inside each one, a lump of plutonium-238 decays steadily, generating heat that thermocouples convert into electricity. In 1977, each spacecraft had about 470 watts of electrical power available, roughly enough to run 4 or 5 household light bulbs. That number has been declining ever since, dropping by about 4 watts per year as the plutonium slowly exhausts itself. You will hear more about this slow fade later, because it is one of the most poignant aspects of the entire mission, a ticking clock that determines how long Voyager can keep whispering to us before it finally goes silent. The launch vehicle chosen for the mission was the Titan III Centaur, a workhorse rocket with a solid track record and just enough lifting power to hurl an 800-kilogram spacecraft onto an escape trajectory from Earth. The Centaur upper stage, fueled by liquid hydrogen and liquid oxygen, provided the final kick needed to reach the speeds necessary for a Jupiter intercept. You picture the rockets falling away one by one, the fairings splitting open like a shell, and Voyager emerging into the sunlight above Earth's atmosphere, its instruments still sleeping, its antenna already searching for the signal from home. Voyager 2 launched on August the 20th, 1977, and Voyager 1 on September 5th. Within weeks, both spacecraft had crossed the orbit of Mars and were accelerating into the asteroid belt, that loose rubble field of rock and metal between Mars and Jupiter. Despite what science fiction movies suggest, the asteroid belt is mostly empty space, and both Voyagers sailed through without incident, which is statistically unsurprising but still a relief. Ahead of them, growing brighter with each passing month, Jupiter waited like a lantern in the dark. You can feel Jupiter before you can see it, or at least that is how you imagine it as you lie here in the dark, your breathing slow and even. The spacecraft's magnetometer starts picking up disturbances months before arrival, faint tugs on the instrument's sensors like the first tremors before an earthquake. Jupiter's magnetic field is the largest structure in the solar system, a vast invisible bubble stretching millions of miles in every direction, so enormous that if you could see it from Earth, it would appear several times wider than the full moon. You're drifting towards something colossal, and the instruments know it before the cameras do. Voyager 1 reaches Jupiter first, making its closest approach on March 5th, 1979. Voyager 2 follows 4 months later in July. Between them, they will take over 33,000 photographs and rewrite nearly every textbook chapter about the largest planet in our solar system. But the images are only part of the story. The real revelations come from the full suite of instruments working together, painting a portrait of a world so violent and so beautiful that it feels almost unfair for one planet to be both. Start with the Great Red Spot, because everyone does. You've seen it in textbook illustrations since childhood, that rusty oval eye staring out from Jupiter's banded atmosphere like a bruise that never heals. Before Voyager, astronomers knew it was a storm, but they did not fully appreciate its scale or its fury. The spot is roughly twice the diameter of Earth. Let that settle into your sleepy brain for a moment. You could drop our entire planet into this storm and still have room for a second one beside it. Wind speeds at its edges reach over 400 miles per hour, and the storm has been raging for at least 350 years, since astronomers first recorded it in the 17th century. Historians still argue whether the spot observed by Robert Hooke in 1664 is the same storm we see today, or a predecessor that faded and was replaced. Either way, Jupiter has been throwing the longest tantrum in recorded science. Voyager's cameras revealed that the Great Red Spot is not a simple whirlpool, but a towering anticyclone, a high-pressure system that rises above the surrounding cloud tops like a mesa above a desert plain. The colours come from complex chemistry, sulfur compounds and phosphorus molecules churned up from deeper layers and cooked by ultraviolet sunlight. The exact recipe remains a matter of scholarly debate even now, which is a polite way of saying nobody's entirely sure why the spot is red. Some researchers favour ammonium hydrosulfide reactions. Others prefer the breakdown of acetylene and ammonia at high altitudes. Jupiter, as usual, keeps its secrets. But the Great Red Spot was familiar territory, a known unknown made sharper by better cameras. The truly staggering discoveries came from Jupiter's moons, and chief among them was Io. You picture this little world, roughly the size of our own moon, orbiting so close to Jupiter that the giant planet fills its sky like a wall of swirling paint. Before Voyager, Io was expected to be a quiet, cratered body, much like the dead moons elsewhere in the solar system. What the camera showed instead was a landscape out of a fever dream. Io is the most volcanically active body in the solar system. Its surface a patchwork of sulfur flows in shades of yellow, orange, red, and black, constantly resurfaced by eruptions so vigorous that not a single impact crater survives. The volcanoes were caught in the act. Navigation engineer Linda Morabito, while processing images to determine Voyager's exact position, noticed a crescent-shaped plume rising nearly 300 kilometers above Io's surface. She had discovered an active volcanic eruption on another world, a first in the history of science. Here is a quirky detail that makes Io even stranger. The volcanic heat is not generated by radioactive decay the way Earth's internal heat mostly is. Instead, Io is being kneaded like bread dough by Jupiter's immense gravitational pull, with additional tugging from the moons Europa and Ganymede. This tidal flexing generates so much friction inside Io that the entire interior remains partially molten. The little moon is essentially being squeezed to death by its own parent planet, which is either a cosmic tragedy or the universe's most aggressive deep tissue massage, depending on your perspective. And then there is Europa, the moon that would launch 1,000 future mission proposals. Europa is slightly smaller than our moon, and its surface is a shell of water ice, crisscrossed by long reddish-brown fractures that give it the appearance of a cracked egg. Voyager's images were tantalizing but limited, just enough to suggest that beneath that ice shell lies a global ocean of liquid water, kept warm by the same tidal heating that tortures Io: water, warmth, and chemistry. The three ingredients that biologists consider necessary for life. You lie there and let that thought drift across your mind like a slow cloud. Somewhere beneath the ice of a moon orbiting a gas giant 778 million kilometers from the Sun, there might be an ocean teeming with something alive. Scientists have been debating the thickness of Europa's ice shell ever since, with estimates ranging from a few kilometers to over 30. The debate is not merely academic. If we ever send a probe to drill through that ice and sample the water below, knowing how far down to dig is rather important. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury, revealed its own surprises. Voyager showed a surface divided into two distinct terrain types: dark, ancient regions pockmarked with craters and lighter grooved terrain suggesting geological activity in the past. Ganymede also turned out to have its own magnetic field, the only moon in the solar system known to possess one, a discovery that hinted at a molten iron core lurking beneath its icy surface. Callisto, the outermost of the four large Galilean moons, presented the opposite extreme, Its surface is among the most heavily cratered in the solar system, a battered face that has changed little in billions of years. Callisto is the quiet sibling who stayed home while the others went out and caused trouble. Jupiter's ring system was another surprise entirely. Before Voyager, nobody knew Jupiter had rings. Saturn was the ringed planet, the showpiece, and Jupiter was supposed to be bare. But Voyager 1's cameras, on a long exposure image looking back toward the Sun, caught a faint thin band of material encircling the planet. The rings turned out to be made of tiny dark particles, likely dust knocked off the inner moons by micrometeorite impacts. They are so tenuous that you could fly through them and never notice, which is essentially what Voyager did. The discovery was a reminder that even the most familiar objects in the solar system can hide features in plain sight, waiting for someone to look from the right angle. As both Voyagers swung past Jupiter, they picked up the gravitational energy they needed to continue onward to Saturn. The encounters had lasted only days in terms of closest approach, but the data would take years to fully analyse. You feel the spacecraft accelerating, pulled forward by stolen momentum, the giant planet shrinking behind them into a bright star. Ahead, fainter but growing, Saturn waits with its magnificent rings spread wide like an invitation. Saturn announces itself with light. Even from hundreds of millions of miles away, the planet gleams in Voyager's cameras like a jewel balanced on a shelf of silk. Those iconic rings catching sunlight and scattering it in ways that make the whole system look almost too elegant to be real. You sink a little deeper into your pillow and imagine the view from the spacecraft's narrow-angle camera as the planet swells from a dot to a disk, to a world so breathtakingly ringed that even the engineers who'd spent years planning for this moment reportedly fell silent when the first high-resolution images arrived on their screens. Voyager 1 reaches Saturn on November 12, 1980. Voyager 2 follows in August 1981. Between them, they will transform Saturn from a beautiful abstraction into a place, a real and complicated system of gas, ice, dust and moons that operates under rules nobody fully anticipated. Start with the rings, because the rings are why you are here, at least partly. Before Voyager, ground-based telescopes and the earlier Pioneer 11 flyby had revealed a handful of broad ring divisions, the A ring, the B ring, the Cassini division, a few others, all seemingly smooth and orderly. Voyager's cameras shattered that tidy picture into thousands of pieces. The rings turned out to be composed of not a few broad bands, but tens of thousands of individual ringlets, some as narrow as a few kilometers across, nested inside each other like the grooves on a vinyl record. The comparison is almost too perfect, given that one of these spacecraft is literally carrying a vinyl record on its side. The complexity was staggering. Some ringlets were circular, others slightly eccentric. Some had sharp edges, others faded gradually. A few displayed baffling kinks and braids, as though someone had reached in and twisted them with invisible fingers. Those invisible fingers turned out to be moons. Voyager discovered what scientists now call shepherd moons, tiny bodies orbiting within or just outside the rings, whose gravitational influence herds ring particles into narrow, well-defined lanes. The moon Prometheus orbits just inside the F ring, and Pandora orbits just outside it, and between them they squeeze the ring material into a tight, sometimes braided strand that looks like a rope seen through a magnifying glass. The F ring in particular became a source of fascination and mild professional headaches, because its structure changed visibly between the Voyager 1 and Voyager 2 encounters just 9 months apart. Rings are not supposed to rearrange themselves on timescales that short, and the discovery forced theorists to rethink how dynamic and alive these structures truly are. here is a mainstream historical fact that puts the rings in context. Galileo first observed Saturn's rings in 1610, but his telescope was so crude that he thought the planet had two large companion bodies, one on each side like ears. He reportedly described it as having a shape resembling a pair of handles on a cup. It took another 45 years before Christian Huygens, using a better telescope, correctly identified the structures as a flat ring surrounding the planet. And it took Voyager more than 3 centuries later to show that Huygens' single flat ring was actually a blizzard of detail that could keep scientists busy for generations. Now here is where things get beautifully strange. Saturn's rings emit radio waves, not because they are broadcasting anything intentional, of course, but because the charged particles trapped in Saturn's magnetic field interact with the ring material and the planet's ionosphere in ways that produce electromagnetic emissions at radio frequencies. Voyager's planetary radio astronomy instrument recorded these emissions, and when scientists converted them to audio frequencies, the result was an eerie, swooping, almost musical sound that rises and falls like a whale song played on a synthesizer. The recordings have been shared widely online, and if you've ever heard them, you know they have a quality that is simultaneously alien and soothing, the kind of sound that belongs in a meditation app designed by extraterrestrials. The exact mechanisms behind all of Saturn's radio emissions are still debated, with some researchers linking certain components to the planet's rotation rate, and others to interactions with the solar wind. Saturn, it turns out, does not make it easy to determine how fast it spins because it has no solid surface to track, and its magnetic field is almost perfectly aligned with its rotation axis, which is unusual and unhelpful. You let that thought wash over you like one of those swooping radio tones, a planet whose own rotation period is uncertain despite centuries of observation. The universe is full of things that refuse to be pinned down. Beyond the rings, Voyager revealed Saturn's atmosphere to be a subtler, more pastel version of Jupiter's. The cloud bands are there, driven by winds that blow even faster than Jupiter's, reaching speeds of over 1,000 miles per hour near the equator. But Saturn's haze layers mute the colours, giving the planet a butterscotch smoothness that hides the violence underneath. Occasional white storm outbreaks punch through the haze every few decades, and Voyager caught hints of these convective upheavals in the data, but the planet's true atmospheric fury would not be fully appreciated until later missions. Among Saturn's moons, several demanded attention. Mimas, the smallest of the major moons, displayed an enormous impact crater named Herschel that covers nearly a third of the moon's diameter, giving it an uncanny resemblance to the Death Star from Star Wars. The movie had been released only a few years before the flyby, and the resemblance was so striking that it became an instant piece of space trivia. Scientists still argue whether the impact that created Herschel came close to shattering Mimas entirely, a question that depends on the moon's internal structure, which remains poorly understood. Enceladus, a small icy moon, showed regions of surprisingly smooth, crater-free terrain alongside older cratered areas, suggesting recent geological activity. Voyager's instruments lacked the resolution to determine what was driving that activity, but the hints were enough to place Enceladus on the list of worlds worth revisiting. Decades later, the Cassini spacecraft would discover geysers of water vapour erupting from Enceladus's south pole, confirming that this little moon harbours a subsurface ocean. Voyager planted the seed of that discovery without ever knowing what it had found, like a detective who photographs the crucial clue but does not develop the film until years later. And then there is the quirky detail that Saturn's rings may be surprisingly young. While Voyager could not settle this question, its measurements of ring mass and composition contributed to a debate that continues today. Some scientists believe the rings formed relatively recently in solar system history, perhaps only 100 or 200 million years ago, meaning that dinosaurs roaming Earth might have looked up at a ringless Saturn if they had possessed telescopes and the inclination to use them. Others argue the rings are primordial, as old as the planet itself, continually recycled by collisions and gravitational interactions. The question remains genuinely open, which is a humbling reminder that even the most photogenic feature in the solar system can keep its age a secret. Voyager 1, its Saturn encounter complete, now tilts upward out of the plane of the solar system, its planetary mission finished but its greater journey just beginning. Voyager 2 still has appointments to keep. But before either spacecraft moves on, there is one more Saturnian world that demands a closer look. A world wrapped in orange haze so thick that not a single photon of visible light reaches its surface. That orange world is Titan, and it is the reason Voyager 1 will never visit another planet. You lie still and let that fact settle. An entire trajectory, the possibility of onward encounters with Uranus and Neptune, sacrificed so that one spacecraft could dive close to a moon shrouded in smog. The decision was not made lightly, and historians still argue whether it was the most scientifically productive trade-off in the history of planetary exploration, or a gamble that paid off only in hindsight. Either way, it was a choice, and it was made because Titan was simply too fascinating to skim past at a distance. Before Voyager, astronomers already knew Titan was special. In 1944, the Dutch-American astronomer Gerard Kuiper had detected methane in Titan's atmosphere using spectroscopy, making it the only moon in the solar system known to possess a substantial atmosphere. But the composition, thickness, and surface conditions beneath that atmosphere remained entirely mysterious. Some scientists speculated that Titan might have a thin methane haze over an icy surface. Others imagined something more dramatic, perhaps oceans of liquid hydrocarbons pooling beneath a dense orange sky. The range of possibilities was so wide that Voyager's Titan flyby was essentially a coin flip between revelation and disappointment. Voyager 1 made its closest approach to Titan on November 12, 1980, passing within about 4,000 kilometers of the moon's cloud tops, and the first thing the cameras revealed was absolutely nothing. Or rather, they revealed a perfectly smooth, featureless orange ball, like a billiard ball dipped in marmalade. The haze was so thick, so uniformly opaque, that not a single surface feature could be detected in visible light. You can imagine the mixture of awe and frustration in the imaging team's lab. They had sacrificed Voyager 1's grand tour for this, and the moon had drawn the curtains. But the other instruments more than compensated. The infrared spectrometer and the radio science experiment, which measured how Voyager's radio signal bent as it passed through Titan's atmosphere, together painted a portrait of a world far more extraordinary than anyone had dared to predict. Titan's atmosphere turned out to be composed primarily of nitrogen, not methane as some had assumed. Nitrogen. The same gas that makes up 78% of the air you are breathing right now as you lie here in the dark. Titan's atmosphere is roughly 95% nitrogen, with methane making up most of the remainder, along with traces of ethane, acetylene, hydrogen cyanide, and a cocktail of other organic molecules complex enough to make a chemist dizzy. And here is the detail that made planetary scientists lose sleep. The surface pressure on Titan is about 1.5 times Earth's sea level pressure. That means if you could somehow stand on Titan's surface, the atmosphere pressing down on you would feel only slightly heavier than the air pressure in your living room. No other moon in the solar system comes remotely close. Titan has a thicker atmosphere than Mars, thicker than Earth in terms of total column mass, and it clings to a body that is smaller than our own planet. The reasons for this atmospheric richness became an immediate subject of study. Titan's low surface temperature, around -179 degrees Celsius, means that gas molecules move sluggishly and are less likely to escape into space. The Moon's respectable gravity, bolstered by its size, helps too. But the ultimate origin of all that nitrogen remains debated. Some researchers believe it was delivered by comets during Titan's formation. Others suggest it was produced by the photochemical breakdown of ammonia over billions of years of solar ultraviolet exposure. The question is one of those beautiful puzzles that Voyager opened without solving. The methane in Titan's atmosphere participates in a cycle that mirrors Earth's water cycle in eerie ways. Ultraviolet sunlight breaks methane apart in the upper atmosphere, and the fragments recombine into heavier hydrocarbons like ethane and acetylene, which drift downward as a kind of organic smog. Some of this material likely rains out onto the surface as liquid methane or ethane. Voyager's data strongly hinted at the possibility of standing liquid on Titan's surface. Perhaps vast lakes or even seas of hydrocarbons sitting beneath that opaque sky. The idea of rain falling on another world, not water rain but hydrocarbon rain, slow and fat and cold, dropping through an orange twilight onto a shore made of water ice as hard as granite, was one of the most poetic images to emerge from the entire Voyager program. Decades later, the Cassini-Huygens mission would confirm those seas, mapping enormous bodies of liquid methane near Titan's North Pole. But in 1980, it was Voyager that first whispered the possibility. A quirky detail about Titan that often gets overlooked involves the Moon's colour. That deep orange hue comes from tholins, complex organic molecules formed when ultraviolet light and energetic particles interact with the methane and nitrogen in the upper atmosphere. Tholins are not a single compound, but a family of sticky, reddish-brown polymers that have been synthesized in laboratories on Earth by mimicking Titan's atmospheric chemistry. Carl Sagan himself coined the term tholin, derived from the Greek word for muddy. These molecules are considered prebiotic, meaning they are the kinds of chemical building blocks that might, under the right conditions, lead to the chemistry of life. Whether Titan's tholins have ever taken that next step is one of the great open questions in astrobiology. The Moon is almost certainly too cold for life as we know it, but scientists still debate whether exotic biochemistries might function in liquid methane environments, using hydrogen in place of oxygen and acetylene in place of glucose. It is speculative, even fringe, but it is not impossible, and that is enough to keep the conversation alive. The radio science data also revealed that Titan's atmosphere has a complex layered structure, with a temperature inversion in the stratosphere and a surface temperature of about 94 kelvins. This precise measurement allowed scientists to calculate that Titan sits right at the triple point of methane, the narrow range of temperature and pressure where methane can exist simultaneously as a solid, a liquid, and a gas. Earth sits at the triple point of water, which is why we have ice, oceans, and clouds all at once. Titan does the same trick with methane, and the parallel is so striking that planetary scientists sometimes call Titan a frozen echo of early Earth, a world where organic chemistry is running wild in slow motion under a dim and distant sun. Voyager 1, its Titan encounter complete, now arcs sharply upward, climbing out of the plane of the solar system at an angle that will carry it toward the northern sky. Its cameras have a few more tasks, a few more moons and ring features to photograph as Saturn recedes. But the planetary sightseeing is over. From here on, the spacecraft's mission shifts from exploration to endurance. It will spend the next 3 decades crossing a vast and seemingly empty stretch of space, waiting for the moment when the sun's influence finally gives way to something else entirely. You feel the quiet settling in, the hush between destinations, and you let your eyes grow a little heavier. Voyager 2, meanwhile, still has places to be. You picture the spacecraft cruising onward past Saturn, carrying its full complement of working instruments and a trajectory that bends not upward but outward, deeper into the solar system toward a planet that most people at the time could barely be bothered to think about. Uranus is the wallflower of the planetary family, the one standing alone at the edge of the party, slightly tilted, saying nothing. And that tilt, as Voyager 2 is about to discover, is the strangest thing about it. The journey from Saturn to Uranus takes 4.5 years. 4.5 years of coasting through darkness, with nothing to photograph, nothing to measure except the gradually thinning solar wind and the faint hiss of cosmic rays. The mission team uses this time to reprogram Voyager 2's computers from across the solar system, uploading new software that will allow the cameras to take longer exposures in the dim light at Uranus. Out here, the sun is barely brighter than a particularly enthusiastic star. Sunlight at Uranus is about 400 times weaker than on Earth, which means photography requires patience, steady hands, and a spacecraft that can hold itself perfectly still while the shutter stays open. The engineers develop a technique called image motion compensation, essentially rotating the entire spacecraft during each exposure to counteract its own movement, a maneuver roughly equivalent to spinning slowly in a desk chair while trying to take a long exposure photograph of a candle across the room. The fact that it works is one of those quiet engineering triumphs that never makes the highlight reels. Voyager 2 arrives at Uranus on January 24th, 1986, and almost immediately the planet begins revealing just how deeply weird it is. The most famous oddity is the axial tilt. Every other planet in the solar system spins with its axis roughly perpendicular to its orbital plane, give or take a few degrees. Uranus, however, is tipped over almost completely on its side. With an axial tilt of about 98 degrees, it essentially rolls around the sun like a ball rather than spinning like a top. The result is a seasonal cycle unlike anything else in the solar system. Each pole spends roughly 42 Earth years in continuous sunlight, followed by 42 years of continuous darkness. When Voyager arrived, the planet's south pole was pointed almost directly at the sun, and the entire southern hemisphere was bathed in perpetual daylight, dim as it was. Nobody's entirely sure what knocked Uranus onto its side. The leading hypothesis involves one or more massive impacts during the planet's formation, collisions with Earth-sized protoplanets that delivered enough angular momentum to tip the whole system over. Historians of science note that this explanation has been around since the 1960s, but scholars still argue about the details. Was it a single catastrophic blow or a series of smaller impacts? Did the tilt happen early in the solar system's history or later? Computer simulations have produced plausible results for both scenarios, which is a polite way of saying the models are flexible enough to support almost any narrative you prefer. Uranus keeps its trauma private. The planet's atmosphere, viewed through Voyager's cameras, was a profound disappointment to anyone hoping for Jupiter-style drama. Uranus appeared as a nearly featureless blue-green sphere, a single colour with almost no banding, no storms, no visible weather of any kind. It looked like a planet that had given up on self-expression. The colour comes from methane in the upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue and green back to the cameras. But beneath that serene exterior, Voyager's instruments detected winds blowing at several hundred miles per hour and a temperature structure suggesting complex atmospheric dynamics hidden beneath the haze. Uranus was not dead. It was just very, very good at keeping a straight face. The magnetic field was where Uranus truly entered the realm of the bizarre. Most planets have magnetic fields that are roughly aligned with their rotation axes. Earth's magnetic poles, for example, are only about 11 degrees off from the geographic poles. Uranus's magnetic field is tilted a staggering 59 degrees away from the rotation axis, and the centre of the field is offset from the planet's core by about a third of the planet's radius. Imagine a bar magnet shoved into a basketball at a steep angle and then pushed off to one side. The resulting magnetic environment around Uranus is chaotic, with a magnetotail that corkscrews through space like a corkscrew, rather than streaming neatly behind the planet. Scientists debated whether this bizarre configuration was a permanent feature, or whether Voyager had caught Uranus in the middle of a magnetic field reversal, a process that happens on Earth every few 100,000 years. The later discovery that Neptune has a similarly wonky magnetic field suggests the offset is a stable feature of ice giant interiors rather than a fluke of timing, but the underlying physics remains an active area of research. Voyager 2 discovered 10 new moons at Uranus, bringing the total known at the time to 15. These are small, dark bodies, most of them only a few tens of kilometers across, orbiting among the planet's rings. The rings themselves had been discovered from Earth in 1977, just months before Voyager's launch, when astronomers observed the planet pass in front of a distant star and noticed the starlight blink on and off several times before and after the occultation. Voyager confirmed and elaborated on the ring system, revealing narrow, dark rings very different from Saturn's bright, broad bands. The Uranian rings are made of very dark material, possibly carbon-rich compounds, and they are remarkably thin and well-defined, maintained by the gravitational influence of shepherd moons lurking nearby. Here is a quirky tidbit that makes Uranus even more endearing in its oddness. The planet's 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are all named after characters from the works of William Shakespeare and Alexander Pope, a tradition started by astronomer John Herschel in the 19th century. This makes Uranus the only planet in the solar system whose moons are named for literary characters rather than figures from Greek or Roman mythology. Miranda, the smallest and innermost of the 5, turned out to be Voyager's most visually stunning discovery at Uranus. Its surface is a geological jigsaw puzzle with enormous fault canyons up to 20 kilometers deep, chevron-shaped ridges, and regions of wildly different terrain types jammed together as though the moon had been shattered and reassembled by a distracted child. One cliff face on Miranda, called Verona Rupes, drops roughly 5 to 10 kilometers straight down, making it one of the tallest known cliff faces in the solar system. In Miranda's weak gravity, an object falling off Verona Rupes would take about 12 minutes to reach the bottom, which is either terrifying or oddly relaxing depending on how you feel about very long falls. Voyager 2 swings past Uranus and bends its trajectory toward Neptune, the last planet on its itinerary. You feel the spacecraft leaning into the curve, borrowing one more handful of gravitational energy and sailing deeper into the cold. Neptune takes 3.5 more years to reach, and during that long coast you can almost feel the darkness thickening around the spacecraft, like a blanket being slowly pulled over your head. The sun, which blazed so fiercely at Jupiter, is now just a very bright star, 900 times dimmer than it appears from your backyard on Earth. The temperature outside the spacecraft hovers around minus 220 degrees Celsius. Everything out here is slow, cold, and patient, which honestly sounds a lot like the ideal conditions for falling asleep, so you are in good company. Voyager 2 arrives at Neptune on August 25, 1989, exactly 12 years after leaving Earth. This is the last planetary encounter of the entire Voyager program, the final curtain call before both spacecraft turn their attention to the long, dark emptiness ahead. And Neptune, as though aware that it is hosting the farewell performance, puts on an absolutely spectacular show. The first surprise is the colour. Neptune is a deep, vivid blue, far more saturated than the pale aquamarine of Uranus. The blue comes from the same methane absorption that colours Uranus, But something else is happening in Neptune's atmosphere, some additional chemical or process that deepens the hue, and scientists still debate exactly what that something is. One hypothesis involves a thinner haze layer that allows you to see deeper into the atmosphere where the methane absorption is stronger. Another points to photochemical products in the upper atmosphere that enhance the blue. The answer probably involves some combination of both, but Neptune has not volunteered a definitive explanation, and nobody has been back to ask since. The second surprise is the weather. Remember Uranus, that placid blue-green marble with the personality of a frozen lake? Neptune is the opposite. Despite receiving even less solar energy than Uranus, Neptune's atmosphere is extraordinarily active, driven by an internal heat source that radiates over 2.5 times more energy than the planet receives from the Sun. This internal furnace powers some of the most extreme weather in the solar system. Voyager's cameras revealed a massive dark storm in Neptune's southern hemisphere, immediately nicknamed the Great Dark Spot in homage to Jupiter's Great Red Spot. The storm was roughly the size of Earth, with wind speeds measured at over 1,200 miles per hour, the fastest winds ever recorded on any planet, 1,200 miles per hour. That is nearly twice the speed of sound on Earth. If you could somehow stand in Neptune's atmosphere, which you very much could not, you would be shredded by winds moving faster than a bullet train before you had time to regret your choices. A mainstream historical fact worth noting is that Neptune's very existence was predicted mathematically before it was ever seen through a telescope. In the 1840s, mathematicians John Couch Adams in England and Urbain Le Verrier in France independently calculated that the gravitational perturbations in Uranus's orbit could be explained by an unseen eighth planet. Le Verrier sent his predictions to the Berlin Observatory, and on September 23, 1846, astronomer Johann Galle pointed his telescope at the predicted location and found Neptune within 1 degree of where the math said it would be. It was one of the great triumphs of Newtonian mechanics, a planet discovered not by looking, but by calculating. And now, nearly a century and a half later, Voyager was seeing it up close for the first and so far, only time. Alongside the Great Dark Spot, Voyager found a smaller storm called Dark Spot 2, or sometimes the Wizard's Eye, and a fast-moving bright cloud feature nicknamed Scooter because of how quickly it raced around the planet. These features demonstrated that Neptune's atmosphere, despite its distance from the Sun, is a dynamic, turbulent place where storms form, migrate, and dissipate on timescales of months to years. When the Hubble Space Telescope observed Neptune a few years after Voyager's flyby, the Great Dark Spot had vanished entirely, replaced by new storms in the Northern Hemisphere. Neptune apparently redecorates frequently. But the true showstopper of the Neptune encounter was not the planet itself. It was Triton, Neptune's largest moon, and one of the most peculiar objects in the solar system. Triton orbits Neptune backward. That is, it moves in the opposite direction from the planet's rotation, a configuration called a retrograde orbit. No other large moon in the solar system does this, and the implication is profound. Triton almost certainly did not form alongside Neptune. Instead, it was captured, probably from the Kuiper belt, that vast ring of icy bodies beyond Neptune's orbit. At some point in the distant past, Triton wandered too close to Neptune and was grabbed by the planet's gravity, dragged into orbit and forced to circle its new home in the wrong direction for eternity. Historians of planetary science point out that the capture hypothesis was proposed long before Voyager, but the flyby provided the observational evidence that made it convincing. Voyager 2 passed within about 40,000 kilometers of Triton's surface, and what it found was breathtaking in the most literal sense. The surface temperature was measured at -235 degrees Celsius, making Triton the coldest surface ever measured by a spacecraft, colder even than Pluto as far as anyone could estimate at the time. The landscape was a frozen wonderland of nitrogen and methane ice, with a pinkish hue from nitrogen frost and a texture in the southern hemisphere that scientists described as cantaloupe terrain, a dimpled, bumpy surface resembling the skin of a melon. Nobody's entirely sure how cantaloupe terrain forms, though some models suggest it results from a process called diaporism, where blobs of less dense ice rise through denser material like wax in a lava lamp. And then there were the geysers. Voyager's cameras spotted dark streaks on Triton's south polar cap, plumes of nitrogen gas erupting from beneath the surface and shooting up to 8 kilometers high before being bent sideways by thin atmospheric winds and deposited as dark trails across the ice. Geysers on a world where the temperature barely climbs above -230 degrees. The mechanism is thought to involve solar heating of subsurface nitrogen ice through a transparent frozen layer, a kind of solid-state greenhouse effect that vaporizes the nitrogen and sends it rocketing upward through vents. It is a quirky and delicate process, a whisper of geological activity on a world that by all rights should be completely inert. You feel the cold of Triton in your imagination, the nitrogen frost glittering under a sun so distant it barely casts shadows. Voyager 2 snaps its final planetary photographs, records its last magnetic field measurements, and bends its course downward below the plane of the solar system, heading south and outward into the unknown. The grand tour is over. Every planet that could be visited has been visited. The data tapes are full, the cameras are tired, and the spacecraft settles into a long, quiet glide. But the mission, as you're about to discover, is far from finished. There is one more photograph to take, and it might be the most important one of all. You lie there in the soft dark and picture the date, February 14th, 1990, Valentine's Day, which feels almost too poetic to be accidental. Voyager 1 is now approximately 6 billion kilometers from Earth, far beyond the orbit of Neptune, sailing through a region of space where the sun is just another star, brighter than the rest but no longer dominant. The spacecraft's cameras have been idle for months. There is nothing out here to photograph. No planets, no moons, no rings, just darkness and the fading breath of the solar wind. And then a command arrives from Earth, travelling at the speed of light for 5.5 hours before reaching the spacecraft's antenna. The command says, in essence, turn around and take one last picture of home. The instruction came at the insistence of Carl Sagan, who had been lobbying NASA for years to use Voyager 1's camera for this purpose. Many at NASA resisted. The photograph had no scientific value, they argued. Pointing the camera back toward the inner solar system meant aiming it dangerously close to the sun, which could damage the Vidicon tube. The spacecraft's time and power were limited resources, and spending them on a sentimental snapshot seemed like an indulgence the mission could not afford. Sagan persisted gently and relentlessly, arguing that the photograph's value was not scientific but human. He believed that seeing Earth from such an enormous distance would change the way people thought about their planet and their place in the universe. Historians of the space program generally credit Sagan's personal relationship with NASA administrators as the decisive factor. Sometimes the most important discoveries are the ones you have to talk someone into making. Voyager 1 rotated its scan platform, aimed its narrow-angle camera back toward the distant sun, and took a series of 60 frames, a mosaic designed to capture as many planets as possible in a single family portrait of the solar system. The images were stored on the spacecraft's tape recorder and transmitted back to Earth over the following weeks. Most of the frames showed nothing remarkable, but one image, taken through a pale blue filter, contained something that would become one of the most famous photographs in human history. In that image, Earth appears as a tiny speck, less than a single pixel wide, suspended in a scattered ray of sunlight that happened to cross the frame like a dusty beam through a window. The planet is so small, so faint, so utterly insignificant against the blackness of space, that you could miss it entirely if no one pointed it out. That pale blue dot, barely visible, is everything. Every person you have ever loved, every war ever fought, every song ever sung, every act of kindness and cruelty, every birth and death and Tuesday afternoon, all of it contained in a mote of dust caught in a sunbeam. Sagan wrote about the photograph with a quiet intensity that has resonated across decades. His words, delivered in lectures and published in his 1994 book, became a kind of secular prayer for the space age, a meditation on humility and fragility that transcended the technical achievement of the image itself. You do not need to quote him to feel the weight of what that photograph communicates. You've seen it. You know what it does to you. It makes you feel small and precious at the same time, which is a trick very few images can pull off. Here is a quirky detail about the pale blue dot that most people do not know. The scattered light beam that makes the photograph so dramatic, that diagonal ray in which Earth appears to float, is not a deliberate artistic effect. It is a lens flare, caused by sunlight bouncing around inside the camera optics. In a purely technical sense, it is an artifact, a flaw. But it is the flaw that makes the image iconic. Without that beam of light, Earth would be just another dim speck in a field of black. With it, the planet looks cradled, almost held, as though the universe is gently presenting it to you and saying, "Look, this is yours, take care of it." Sometimes the best art is accidental. The family portrait mosaic also captured Venus, Jupiter, Saturn, Uranus, and Neptune, though Mars and Mercury were too close to the Sun to be visible, and Pluto was too faint. Together, the images form a kind of farewell snapshot, the solar system seen from the outside for the first time. Scientists still argue about the precise distance from which the images were taken, with estimates ranging from about 6 billion to 6.4 billion kilometers, depending on which frame you reference and how you calculate the spacecraft's position. The uncertainty is itself a reminder of how far away Voyager was. At that distance, pinpointing your exact location becomes an exercise in very precise guesswork. After the photographs were taken, NASA sent a final command to Voyager 1's cameras. They were powered off permanently. The electricity they consumed was needed for the instruments that would matter in the decades ahead. The magnetometer, the plasma wave detector, the cosmic ray counter. The eyes closed, but the ears stayed open. Voyager 1 would spend the next 20+ years listening to the space around it, feeling the magnetic fields, counting the particles, sensing the gradual weakening of the Sun's influence as the spacecraft pushed deeper into the boundary region where our star's dominion ends and the galaxy begins. You let that image linger behind your closed eyelids, a tiny blue dot, a spacecraft moving away from it at 17 kilometers per second, a camera shutting down for the last time, and ahead, nothing but the slow fade of the solar wind and the growing whisper of interstellar space. The pale blue dot photograph is not a discovery in the traditional sense. It did not reveal a new moon, or a new ring, or a new atmospheric composition. But it discovered something about us, about our smallness and our stubbornness, and our need to look back even as we move forward. And that, in the quiet math of human meaning, may be worth more than any spectrometer reading ever taken. The spacecraft drifts on, camera blind but sensor alert, And the next phase of its journey, the one nobody planned for and everyone hoped would happen, is about to begin. The edge of the solar system is not a line on a map. It is a gradual, messy, contested boundary, and Voyager is about to spend decades figuring out exactly where it is. The edge of the solar system is not a cliff. You might imagine it that way, a neat border where sunlight ends and starlight begins. A cosmic fence with a little gate, and maybe a sign that reads, "You're now leaving the heliosphere, thank you for visiting." But nature does not do clean edges, and the boundary between our sun's domain and interstellar space is more like a shoreline than a wall, a turbulent, shifting, messy zone where two vast oceans of charged particles push against each other in a slow and silent contest that's been going on for billions of years. To understand what Voyager found out here, you need to understand what it was flying through. The sun does not just emit light, it exhales. A constant stream of charged particles, mostly protons and electrons, flows outward from the sun's corona at speeds ranging from 300 to 800 kilometers per second. This is the solar wind, and it fills a vast bubble around the sun called the heliosphere. Inside the heliosphere, the sun's magnetic field and particle output dominate the local environment. Outside the heliosphere, the interstellar medium takes over, a thin soup of gas and dust and cosmic rays that fills the space between stars and answers to the magnetic fields of the galaxy itself. The boundary between these two regions is what Voyager has been slowly, painstakingly crossing for decades, and the crossing turned out to be far more complicated than anyone expected. The first major landmark is called the termination shock, and Voyager 1 crossed it in December 2004, roughly 27 years after launch. You picture the moment, though of course, there was no visible flash, no dramatic jolt. What happened was more subtle and more profound. The solar wind, which had been flowing outward at supersonic speeds for billions of kilometers, suddenly slowed down. It didn't stop. It decelerated abruptly from supersonic to subsonic, piling up and compressing like traffic hitting a bottleneck on a highway. The spacecraft's instruments registered a sharp increase in the magnetic field strength and a corresponding spike in the density and temperature of the surrounding plasma. Voyager 1 had entered the heliosheath, the thick, turbulent layer of compressed solar wind that forms the outer lining of the heliosphere. Here is a mainstream historical fact that gives this moment some context. The existence of the termination shock was predicted theoretically in the 1960s, decades before any spacecraft was in a position to detect it. Astrophysicists had modelled the interaction between the solar wind and the interstellar medium and concluded that there must be a point where the outward flow of solar particles slows to subsonic speeds, much like the shock wave that forms in front of a supersonic jet. But the distance to this boundary was poorly constrained. Estimates range from as close as 50 astronomical units to well over 100, where 1 astronomical unit is the distance from the Earth to the Sun. Voyager 1 found it at about 94 astronomical units, roughly 14 billion kilometers from the Sun, which was comfortably within the predicted range but still carried the satisfaction of turning a theoretical construct into a measured reality. Voyager 2, travelling on a different trajectory through the southern hemisphere of the heliosphere, would cross the termination shock 4 years later, in August 2008, at a distance of about 84 astronomical units. The fact that the two crossings happened at different distances was itself a discovery. It meant the heliosphere is not a perfect sphere. The termination shock is closer to the Sun in some directions than others, pushed inward by variations in the pressure of the interstellar medium. The heliosphere, it turns out, is lopsided, squished by the galactic environment like a balloon pressed against a wall. Scientists still argue about the exact shape, a debate that will grow louder in later sections of this journey, but the asymmetry was undeniable. Inside the heliosheath, things got strange. You imagine Voyager 1 pushing through this compressed region, its instruments recording a plasma environment that behaved in ways nobody had fully anticipated. The solar wind, now slowed to a crawl, became turbulent and chaotic. The magnetic field fluctuated wildly. The temperature of the plasma was far higher than expected, heated by the compression at the termination shock to over 1 million degrees. This might sound alarming, but remember that temperature in a plasma is a measure of how fast the particles are moving, not how much total heat energy is present. The plasma out here is so thin, so sparse, that you could fly through million-degree material and feel nothing at all. It is the loneliest kind of heat, intense on a per-particle basis, but spread so thin it might as well be cold. A quirky detail about the termination shock crossing is that scientists almost missed it. Voyager 1's plasma science instrument, the one device best suited to directly measure the solar wind speed, had stopped working back in 1980, a casualty of the intense radiation environment around Jupiter. Without it, the termination shock had to be inferred from indirect measurements, changes in magnetic field strength, increases in energetic particle counts, and subtle shifts in the plasma wave data. It was like trying to determine the exact moment you crossed a state line while driving blindfolded, relying only on the change in road texture and the fading signal of a local radio station. The scientists managed it, but the ambiguity introduced a layer of scholarly debate about the precise timing and location of the crossing that persisted for years. Voyager 2, crucially, still had its plasma science instrument working. When it crossed the termination shock in 2008, it provided the first direct measurement of the solar wind speed dropping from supersonic to subsonic. The data confirmed what Voyager 1 had inferred but could not prove, and it gave scientists a cleaner, more complete picture of what happens at this boundary. You feel a small satisfaction in that, the two spacecraft complementing each other across decades and billions of kilometers, one filling in the gaps that the other could not. The heliosheath is not a thin membrane. It is a thick, turbulent region that Voyager 1 would spend the next 8 years traversing before reaching the next boundary. During that long slog, the spacecraft measured gradual changes in the particle environment, the slow decline of solar wind particles, and the equally slow rise of galactic cosmic rays leaking inward from interstellar space. The transition was not smooth. It came in fits and starts, with sudden jumps and unexpected reversals, as though the boundary between sun and galaxy were breathing, expanding and contracting in response to changes in solar activity. You picture it as a living membrane, pulsing gently in the dark, and the spacecraft as a tiny needle slowly pushing through it, recording every tremor. Somewhere in the outer reaches of the heliosheath, Voyager 1 stumbles into a region that nobody predicted and nobody can quite explain. You lie still and let the strangeness of it settle over you like a second blanket. The year is 2012, and the spacecraft is roughly 122 astronomical units from the Sun, about 18 billion kilometers from the front porch, where you might sit on a summer evening and watch the stars come out. The instruments have been recording a gradual shift in the particle environment for months, the usual slow dance of declining solar particles and rising cosmic rays that signals the approach of the heliosphere's outer boundary. And then, in late July, something unexpected happens. The cosmic ray count jumps sharply, solar particles drop. For a brief, tantalizing period, it looks as though Voyager 1 might have crossed the heliopause, the outermost boundary of the heliosphere, and entered interstellar space. But then the readings reverse. Cosmic rays dip back down, solar particles recover. A few days later, The same pattern repeats: jump, drop, reverse, repeat. The spacecraft appears to be bouncing in and out of some transitional zone, crossing a threshold and then retreating, like someone standing in a doorway and being unable to decide whether to step inside or stay out. Mission scientists, puzzled and cautious, begin calling this region the magnetic highway. The name comes from the behavior of charged particles in the zone. Instead of the usual disordered mix of solar and galactic particles sloshing around in the heliosheath, the magnetic highway shows a striking pattern. High-energy particles from outside the solar system stream inward along magnetic field lines, while lower-energy solar particles stream outward along the same lines, as though the magnetic field has opened a set of lanes connecting the heliosphere to the galaxy beyond. The particles are organized, sorted by energy and direction, flowing along connected field lines like cars on a highway with clearly marked lanes, hence the name. Here is what makes the magnetic highway so puzzling. The magnetic field direction did not change. In the heliosheath, the magnetic field points roughly in one direction, shaped by the sun's rotation and the outward flow of the solar wind. If Voyager 1 had truly crossed into interstellar space, scientists expected the magnetic field to rotate sharply, reflecting the different orientation of the galactic magnetic field. But in the magnetic highway, the field direction remained stubbornly solar. The particles said interstellar, the magnetic field said heliosphere. The spacecraft was sending contradictory signals, and the scientific community responded with the academic equivalent of a heated family dinner argument. Some researchers argued that the magnetic highway was simply the outermost layer of the heliosheath, a boundary region where the sun's magnetic field was still dominant, but galactic particles had begun to leak through like water seeping under a door. Others proposed that the heliosphere's outer boundary was not a single sharp surface, but a series of nested layers, each with its own particle and field characteristics, and that the magnetic highway was one of these intermediate layers that models had not anticipated. A few more adventurous theorists suggested that the magnetic field data was misleading, that the galactic and solar magnetic fields might happen to be aligned in this particular direction, making the transition invisible to the magnetometer, even though the spacecraft had already crossed it. Historians of space science note that the debate over the magnetic highway was not merely a technical disagreement, but a philosophical one about what it means to leave the solar system. Where exactly is the border? If the sun's magnetic field extends beyond the point where solar particles give way to galactic ones, does the heliosphere end where the particles change or where the field changes? Is the boundary defined by composition or by geometry? It is the kind of question that sounds abstract, until you realise that the answer determines whether Voyager 1 has achieved one of the most symbolically significant milestones in human history, or is still a few billion kilometres short. A quirky detail about this period is that the magnetic highway was not predicted by any of the major heliospheric models. The theoretical frameworks that scientists had built over decades to describe the interaction between the solar wind and the interstellar medium simply did not include this region. It was a genuinely new phenomenon, discovered not in a laboratory or a computer simulation, but by a 40-year-old spacecraft running on the electrical equivalent of a dim light bulb. The models were not wrong exactly. They were incomplete, which in science is the most common and most productive kind of wrong. Voyager 1 spent several months in the magnetic highway, its instruments recording repeated oscillations between solar-dominated and galactic-dominated particle environments. Each oscillation generated a fresh round of analysis and debate on Earth. Papers were published, press conferences were held, and the phrase, "Has Voyager left the solar system?" became a recurring headline in science journalism, often answered with some variation of "it is complicated." scholars still argue about the exact physical mechanism that creates the magnetic highway. One popular model involves magnetic reconnection, a process where opposing magnetic field lines snap and reconnect, creating temporary openings through which particles can flow freely between the heliosphere and interstellar space. Reconnection is a well-known phenomenon in solar physics, responsible for solar flares and coronal mass ejections, but its role at the edge of the heliosphere was not widely appreciated until the magnetic highway forced scientists to consider it. You picture the magnetic field lines out there, invisible threads stretching across billions of kilometers, occasionally snapping and reweaving themselves like a cosmic loom operated by a weaver with trembling hands. Along those threads, particles stream in both directions, galactic travelers heading inward and solar refugees heading out, each following the magnetic contours of a boundary zone that is neither fully inside nor fully outside the Sun's domain. It is a liminal space, a threshold region, and Voyager 1 is caught in it, oscillating back and forth like a dreamer hovering between sleep and waking. The spacecraft does not know it is confused. It does not know anything at all. It simply measures what is around it and sends the numbers home at the speed of light, trusting that someone on the other end will figure out what the numbers mean. And the people on the other end, sitting in offices at JPL and universities around the world, are doing their best, squinting at graphs and arguing over coffee, trying to decipher a message from the edge of everything. You feel your own eyelids growing heavier, and you let the image of those streaming particles carry you a little closer to sleep. The magnetic highway hums beneath the spacecraft like a lullaby played on invisible strings, and somewhere ahead, beyond the last oscillation, the true boundary waits. The crossing happens quietly, as most truly important things do. You're lying in the dark, half dreaming, and somewhere 18.2 billion kilometers away, Voyager 1 slips through the last layer of the Sun's influence and enters the space between the stars. The date, reconstructed later from careful analysis of the data, is August 25th, 2012. But nobody on Earth knows it yet. Nobody will know it for over a year because the data is ambiguous, the instruments are old, and the scientific community is engaged in one of the most painstaking and contentious debates in modern space science. Here is what the instruments recorded. In late August 2012, the count of galactic cosmic rays jumped sharply and stayed high. Simultaneously, the count of solar energetic particles, the lower energy particles that originate from the Sun, dropped to near zero and stayed there. This was the particle signature that scientists had been waiting for, the definitive swap from solar-dominated to galactic-dominated that should mark the heliopause. But remember the magnetic highway and its contradictory signals. The magnetic field direction still did not change in the way models predicted. It rotated slightly, yes, but not the dramatic shift that would clearly indicate a transition from the Sun's magnetic domain to the galaxies. The data was saying two different things, and scientists were understandably reluctant to make a historic announcement based on incomplete agreement among the instruments. The breakthrough came from an unexpected source. In April 2013, a coronal mass ejection, a massive belch of magnetized plasma from the Sun launched months earlier, finally reached Voyager 1's location and disturbed the plasma around the spacecraft. The plasma wave instrument, one of the few detectors still functioning, recorded oscillations in the electron density of the surrounding medium. These oscillations allowed scientists to calculate the local plasma density for the first time in years, and the number they got was startling. The density was roughly 40 times higher than anything measured inside the heliosheath. This was consistent with the theoretical density of the interstellar medium, and wildly inconsistent with the density expected inside the heliosphere. The plasma was interstellar. Voyager 1 was outside. The team, led by Don Gurnett at the University of Iowa, published their findings in September 2013 in the journal Science. Using the plasma density measurements, they back-calculated the probable crossing date to August 25, 2012, give or take a day. The announcement made headlines around the world. Voyager 1 had become the first human-made object to reach interstellar space. 40 years after a group of engineers in Pasadena bolted a golden record to the side of a spacecraft and aimed it at Jupiter, that spacecraft had left the building. Not just the building, but the entire neighborhood, the city, the continent, the planet's whole sphere of influence. It was out there now, in the space between stars, carrying whale songs and Beethoven, and a recording of Androian's brainwaves into a void that stretches for light years in every direction. But even after the announcement, the debate did not end. A mainstream historical fact that deserves attention is that NASA itself was cautious about the language. The official statement said, Voyager 1 had entered interstellar space, but some scientists argued that it had not truly left the solar system, because the solar system can be defined in different ways. If you define the solar system's boundary as the heliosphere's edge, then yes, Voyager 1 was out. But if you define it as the outer limit of the Sun's gravitational influence, then the spacecraft has barely started the journey. The Oort cloud, that hypothetical shell of icy bodies loosely bound to the Sun, is thought to extend out to perhaps 100,000 astronomical units, nearly 2 light-years from the Sun. Voyager 1, at 122 astronomical units, had crossed just over 1/10% of that distance. By the gravitational definition, Voyager will not leave the solar system for another 30,000 years. Scholars still argue about which definition is more meaningful, and the answer depends largely on whether you're a heliophysicist or a dynamicist, which is one of those disciplinary divides that can make academic conferences surprisingly lively. A quirky detail about the crossing announcement is the role that sound played in communicating it to the public. Don Gurnett's team converted the plasma oscillation data into audible frequencies, producing a rising tone that represented the increasing electron density as Voyager moved from the heliosphere into interstellar space. The sound was eerie, a low hum climbing gradually to a higher pitch, like a tuning fork being slowly tightened. It became the unofficial soundtrack of the crossing, played on news broadcasts and shared millions of times online. There is something deeply satisfying about the idea that the first sounds of interstellar space were heard not through a microphone but through a mathematical conversion of electrical field measurements into something your ears could process. The universe does not make sound in a vacuum, but if you translate its data cleverly enough, it sings. The magnetic field question, meanwhile, was eventually resolved, sort of. Further analysis showed that the magnetic field direction at the heliopause was indeed influenced by the interstellar medium, but that the transition was far more gradual and less dramatic than models had predicted. The galactic magnetic field in Voyager, one's vicinity turned out to be roughly aligned with the heliospheric field at the crossing point, which explained why the magnetometer did not register a sharp change. It was less like walking through a door, and more like wading from a blue pool into a green one, where the water happens to be flowing in the same direction. The boundary was real, but its magnetic signature was subtle, and detecting it required the kind of careful, multi-instrument analysis that took over a year to complete. You let the significance of August 25, 2012 wash over you. A machine built by human hands, powered by decaying plutonium, guided by 69 kilobytes of memory, communicating through a 23-watt transmitter, had reached interstellar space. It had taken 35 years. The signal confirming the crossing took 17 hours to reach Earth, travelling at the speed of light across a distance so vast that your brain cannot meaningfully comprehend it, only approximate it with numbers that look more like typos than measurements. And yet the signal arrived, faint but clear, picked up by a 70-metre dish in the Australian outback, decoded by computers in Pasadena, and turned into a press release that made the whole world pause for a moment and look up. The spacecraft, of course, felt nothing. It simply kept going, measuring what was around it, sending the numbers home. But you feel something, lying here in the dark, a small quiet pride in belonging to a species that would even attempt such a thing. The stars outside your window are no longer entirely out of reach. One tiny piece of Earth is out there among them now, and it is still talking. The first thing you notice about interstellar space is that it is not empty. You might have expected silence, a perfect vacuum, the kind of absolute nothingness that poets and philosophers have projected onto the void between stars for centuries. But Voyager 1's instruments tell a different story. The space out here hums. It vibrates with a low, persistent plasma oscillation that reveals a medium far denser and more structured than the near vacuum inside the heliosphere. You're not floating in nothing. You're swimming in something, a thin but measurable ocean of ionized gas that fills the galaxy like water fills a bathtub, invisible to the eye, but undeniably present to any instrument sensitive enough to feel it. The plasma wave instrument aboard Voyager 1, originally designed to study the electromagnetic fields around Jupiter and Saturn, has become the mission's star performer in this late chapter. It detects oscillations in the electric field caused by electrons vibrating in the surrounding plasma, and the frequency of those oscillations is directly related to the density of electrons in the medium. Inside the heliosphere, the electron density was low, typically around 0.002 electrons per cubic centimetre. When Voyager crossed the heliopause, that number jumped to about 0.08, a 40-fold increase. In absolute terms, this is still extraordinarily thin. A cubic centimetre of air at sea level on Earth contains roughly 25 billion molecules. A cubic centimetre of interstellar space near the heliopause contains fewer than 1/10 of one electron. But in the context of deep space physics, that difference between inside and outside the heliosphere is enormous, and it carries profound implications for how the galaxy works. The density measurements came in bursts, triggered by events on the Sun. When the Sun emits a particularly powerful coronal mass ejection, a blast wave of magnetized plasma races outward through the solar system at hundreds of kilometers per second. By the time it reaches Voyager's position, it has been travelling for over a year, weakened and spread thin but still energetic enough to jostle the interstellar plasma and set it ringing. Each time one of these disturbances arrived, Voyager's plasma wave instrument recorded the resulting oscillations, and each time the calculated density was consistent with interstellar values. The medium between the stars was declaring itself vibration by vibration, like a bell being struck at irregular intervals by a very distant and very slow hammer. When scientists converted these plasma oscillations to audio frequencies, the results became one of the most shared and discussed pieces of Voyager data in the entire mission. The sound is haunting. You can find it online, a low drone that shifts in pitch as the plasma density changes, punctuated by sharper tones when solar disturbances pass through. Some people describe it as a hum. Others say it sounds like a Tibetan singing bowl played in slow motion. A few more creative listeners have compared it to the background noise of a submarine sonar room, a constant ambient presence that tells you something vast and invisible surrounds you on all sides. Whatever metaphor you prefer, the sound is real, in the sense that it represents real physical vibrations in a real medium. The universe between the stars is not silent. It murmurs. A mainstream historical fact worth pausing over is that the existence of the interstellar medium has been known, in broad strokes, for over a century. Astronomers in the early 1900s noticed that the light from distant stars was slightly reddened and dimmed, indicating that something between the stars was absorbing and scattering the light. By the mid-20th century, radio astronomers had mapped vast clouds of neutral hydrogen gas filling the galaxy, and theorists had developed detailed models of how this gas interacts with stellar winds and supernova remnants. But all of this knowledge was remote, inferred from observations made at enormous distances. Voyager 1 is the first instrument to be physically immersed in the interstellar medium and measure it directly. The difference between observing something from far away and sticking your hand into it is the difference between reading about the ocean and tasting salt water. The interstellar medium near the heliopause is not uniform. Voyager's data shows that the density fluctuates over time and space, sometimes gradually, and sometimes in sharp jumps. Some of these fluctuations correlate with solar events. The pressure waves from coronal mass ejections compressing the local plasma and raising its density temporarily. Others appear to reflect genuine variations in the interstellar medium itself, clumps and voids in the galactic gas that Voyager is drifting through, like a boat crossing a lake with uneven currents. Scientists still argue about the relative importance of solar-driven and interstellar-driven density variations. Untangling the two requires careful timing analysis, matching each density jump to a known solar event and seeing what is left over. The leftover signal, the part that cannot be explained by the sun, is the voice of the galaxy speaking directly. Here is a quirky detail that illustrates just how thin the interstellar medium really is. If you took all the interstellar gas in a volume of space the size of Earth, compressed it into a solid block, and weighed it, the result would be roughly the mass of a small asteroid, perhaps a kilometre across. The interstellar medium is so sparse that it makes the best laboratory vacuums on Earth look crowded by comparison. And yet this near-nothing medium is responsible for some of the most important processes in galactic evolution. It is the raw material from which new stars form. It carries magnetic fields that shape the structure of spiral arms. It absorbs and re-emits energy at wavelengths that tell astronomers about the chemical composition and physical conditions of the galaxy. The interstellar medium is to the Milky Way what blood is to a body, a thin, circulating fluid that connects everything and sustains the whole. Voyager 1 continues to drift through this medium, its plasma wave instrument listening, its magnetometer feeling the gentle tug of galactic magnetic fields, its cosmic ray detectors counting the high-energy particles that rain through interstellar space from distant supernovae and active galactic nuclei. Each measurement is a sentence in a message from the galaxy, transmitted at 160 bits per second through a 23-watt radio signal across 18 billion kilometers of void. The data arrives at Earth as a whisper, barely distinguishable from the background noise of the universe, and teams of engineers and scientists amplify it, decode it, and transform it into knowledge. You let the hum of interstellar plasma fill your imagination, a low and constant tone vibrating through the dark. The space between the stars is not empty. It is full of secrets, and Voyager is listening to them one oscillation at a time, sending each one home like a postcard from the farthest shore anyone has ever reached. 6 years after its twins slip through the heliopause, Voyager 2 reaches the same boundary and steps across. The date is November 5th, 2018, and the spacecraft is approximately 119 astronomical units from the Sun, about 17.7 billion kilometers out, travelling in a different direction than Voyager 1 through a different hemisphere of the heliosphere. The two crossings are separated by 6 years, 6 billion kilometers, and a fundamental difference in instrumentation that makes Voyager 2's exit arguably more scientifically valuable than its siblings, even if it happened second and received slightly less fanfare. The critical difference is the plasma science instrument. Remember that Voyager 1's plasma detector failed back in 1980, a victim of Jupiter's punishing radiation belts. Voyager 2's instrument survived, and it has been quietly working for over 4 decades, measuring the speed, density and temperature of the charged particles flowing around the spacecraft. When Voyager 2 crosses the heliopause, this instrument provides the first direct measurement of what happens to the solar wind at the very edge of its influence. It measures the moment the solar wind stops entirely, not inferred from magnetic field changes or cosmic ray counts or plasma wave oscillations, but directly observed as a drop to zero in the outward flow of solar particles. The wind from the sun, which has been blowing past the spacecraft for 41 years, simply ceases. You imagine that sensation, the sudden stillness after a lifetime of breeze, and it feels like the moment an airplane's engines shut off and you're left gliding in pure silence. But Voyager 2 measures something else that nobody quite expected. The temperature of the plasma just inside the heliopause is far hotter than models predicted, reaching tens of thousands of degrees in the compressed Helios Heath region near the boundary. This is not the gentle cooling you might expect at the outermost fringes of the sun's influence. Instead, the plasma is being heated by the compression of the solar wind against the interstellar medium, squeezed and energized at the boundary like toothpaste forced against the sealed end of a tube. The temperature data from Voyager 2's working instrument provides a constraint that Voyager 1 simply could not offer, and it immediately sends theorists back to their models to figure out why the boundary layer is so hot. On the interstellar side, Voyager 2's plasma instrument measures the temperature and density of the local interstellar medium directly. The density is broadly consistent with what Voyager 1's plasma wave instrument inferred, roughly 0.05 to 0.09 electrons per cubic centimetre, confirming that the interstellar medium near the heliopause is indeed denser than the heliosheath by a significant factor. But the temperature of the interstellar plasma is lower than expected, around 6,000 to 7,000 degrees Celsius, which sounds scorching, but is actually cooler than some models predicted for this region. Scholars still argue about whether this cooler temperature reflects the general conditions of the local interstellar cloud through which the sun is moving, or whether it indicates some cooling process at the heliospheric boundary that has not been adequately modelled. The data from a single point in space is precious but limited. It tells you what the medium is like right here, right now. But extrapolating from one location to the broader interstellar environment requires caution and a tolerance for uncertainty. A mainstream historical fact about Voyager 2's crossing is that it was detected in near real time, unlike Voyager 1's crossing, which was only confirmed retrospectively over a year later. By 2018, the mission team had learned what to look for. They watched the cosmic ray counts climb and the solar particle counts fall, recognized the signatures from Voyager 1's experience, and were able to announce the crossing within weeks. The press coverage was celebratory but slightly muted compared to 2013, the way second achievements often are. The first person to climb a mountain gets the monument. The second person to climb it with better equipment and more detailed notes gets a paragraph in the methodology section. But in terms of pure scientific value, Voyager 2's crossing may ultimately prove more important because of that working plasma instrument, a piece of hardware that has been functioning since the Carter administration and is still delivering data that reshapes our understanding of the galaxy's doorstep. Here is a quirky detail about the timing. Voyager 2 crossed the heliopause at a distance about 3 astronomical units closer to the Sun than Voyager 1 did. This confirms that the heliosphere is not symmetrical. The boundary is closer in the direction Voyager 2 was travelling, which corresponds to a region where the pressure from the interstellar medium is slightly higher, pushing the heliopause inward. Imagine a soap bubble being blown sideways by a gentle wind. The side facing the wind gets pushed in, while the far side stretches out. The heliosphere behaves similarly, compressed on one side by the flow of interstellar gas and magnetic pressure, and elongated on the other. The two Voyager crossings taken together provide 2 data points on the shape of this bubble, separated by roughly the maximum possible distance at the same boundary. 2 points do not make a map, but they mark the beginning of one. Voyager 2 also observed something fascinating in the days just before and after the crossing. The magnetic field at the heliopause exhibited a distinct boundary layer, a thin region where the field strength increased sharply, much more clearly defined than what Voyager 1 had observed. This suggests that the heliopause at Voyager 2's crossing point was relatively clean, sharp boundary, almost like a wall of compressed magnetic field separating the solar and interstellar domains. Whether this sharpness is a local feature of Voyager 2's crossing point or a general characteristic of the heliopause remains uncertain. Scientists suspect the answer may depend on local conditions, the angle of the interstellar magnetic field, the level of solar activity at the time of crossing, and possibly the recent history of coronal mass ejections that may have swept past and temporarily reshaped the boundary. You let the 2 crossings sit side by side in your mind. Voyager 1 in 2012, crossing blindly with a broken plasma instrument and a magnetic field that refused to cooperate with expectations. Voyager 2 in 2018, crossing with cleaner data, sharper instruments, and the benefit of its twins' hard-won experience. Together they bracket the heliosphere like bookends, one high and one low, one early and one late, each telling a slightly different version of the same story. The sun's bubble has an edge. It is real, it is messy, and it is not the same everywhere. And beyond it, the galaxy waits with a temperature and a density and a magnetic field of its own, measured now not by inference but by touch. The spacecraft drift apart in the dark, each following its own trajectory into a medium that, for the first time in human history, someone is actually there to taste. Now that both spacecraft have crossed the heliopause, a question that had been simmering in the background for decades boils over into one of the most entertaining debates in heliophysics. What shape is the heliosphere? You might think this would be a straightforward question. The sun blows a bubble, the interstellar medium pushes back, and the resulting shape should be calculable from basic physics. But the reality is that 50 years of modelling have produced at least half a dozen competing shapes, and the Voyager data, rather than settling the argument, has managed to make it louder. The traditional picture, the one you probably saw in a textbook at some point, shows the heliosphere as a comet-shaped structure. The sun moves through the interstellar medium at about 23 kilometers per second, and the flow of interstellar gas around the heliosphere compresses the front, the nose, into a blunt curve while stretching the back into a long tail that trails behind for hundreds or even thousands of astronomical units. This comet model was the dominant view for decades, and it has a satisfying visual elegance. You can imagine the sun as a boat pushing through a river, with a bow wave at the front and a wake streaming behind. The heliosphere's nose, where the interstellar wind hits first, should be where the heliopause is closest to the sun. The tail, sheltered from the wind, should extend much farther out. The two Voyager crossings, both occurring in the general nose direction, are broadly consistent with this picture. But in 2015, a team of researchers led by Merav Ofer at Boston University published a paper that proposed something radically different. Using magnetohydrodynamic simulations that incorporated the effects of neutral atoms, pickup ions, and the asymmetric pressure of the interstellar magnetic field. They argued that the heliosphere does not have a long tail at all. Instead, they proposed that the heliosphere is shaped roughly like a croissant, a fat crescent-shaped structure with two rounded lobes extending behind the Sun rather than a single elongated tail. The two lobes are produced by the interaction between the solar magnetic field, which reverses polarity every 11 years with the solar cycle, and the flow of the interstellar medium. The jets of solar wind emanating from the Sun's poles get deflected and rolled up by the interstellar flow, creating the twin-lobed structure, a croissant, floating in the galaxy, protecting you from cosmic radiation. If that does not make you smile a little as you lie here in the dark, you may already be asleep. The croissant model was controversial from the start. Scholars still argue vigorously about whether the data supports it, and the debate has produced some of the most colourful exchanges in recent heliophysics literature, which is saying something for a field not generally known for drama. Critics of the croissant model point out that the simulations depend sensitively on assumptions about the interstellar magnetic field, strength and orientation, quantities that are poorly constrained by observation. Change the field parameters slightly, and the croissant becomes a deflated balloon, or a jellyfish, or something with no obvious pastry analogue at all. Supporters counter that the traditional comet model has its own set of unrealistic assumptions, including the treatment of the heliosphere as a simple, gas dynamic problem, when it is actually a complex plasma environment where magnetic fields, neutral atoms, and energetic particles all play competing roles. A mainstream historical fact that grounds this debate is that the first models of the heliosphere's shape were developed in the 1960s, when computing power was so limited that the calculations had to be done in 2 dimensions. These early models naturally produced axially symmetric shapes, cones and paraboloids that looked neat on paper but could not capture the 3-dimensional messiness of the real interaction. As computers grew more powerful, the models grew more complex, incorporating magnetic fields, time-varying solar wind conditions, and the effects of charge exchange between solar wind protons and interstellar neutral hydrogen. Each added layer of physics produced a slightly different shape, and by the time the Voyager crossings provided actual data points, there were so many competing models that the 2 measurements could be claimed as support by almost anyone. Here's a quirky detail that makes the shape debate even more entertaining. Some models predict the existence of a feature called the heliotail instability, a region far downstream from the Sun where the elongated tail of the heliosphere becomes unstable and breaks up into turbulent eddies, like the wake of a boat dissolving into swirls far behind the stern. If this instability exists, it means the heliosphere does not have a clean trailing edge at all. It just frays and dissolves into the interstellar medium, which makes defining the shape of the tail a bit like trying to define the shape of smoke rising from a candle. At some point, the smoke is no longer smoke, it is just air with a memory. The Voyager data alone cannot resolve the shape question. Both spacecraft crossed the heliopause in the nose region, within roughly 30 degrees of the direction the Sun is moving through the interstellar medium. They tell us what the front of the heliosphere looks like, but they say nothing about the sides, the tail, or the overall 3-dimensional geometry. To map the complete shape, you would need multiple spacecraft exiting in different directions, a fleet of Voyagers aimed at different corners of the sky. No such fleet exists, and none is currently planned, though proposals for an interstellar probe mission have been circulating in the planetary science community for years. Until such a mission flies, the shape of the heliosphere will remain constrained by 2 data points and a lot of very sophisticated guesswork. Remote observations have tried to fill the gap. NASA's Interstellar Boundary Explorer, a small satellite orbiting Earth, maps the heliosphere's boundary by detecting energetic neutral atoms that are produced when solar wind particles interact with interstellar hydrogen at the edge of the heliosphere. These atoms, uncharged and therefore unaffected by magnetic fields, fly in straight lines back toward Earth and can be used to construct a rough image of the boundary, like mapping the walls of a dark room by throwing tennis balls and listening for the bounce. The images produced by this technique are blurry and ambiguous, but they suggest a heliosphere that is somewhat flattened and asymmetric, which is consistent with both the comet and the Poisson models, depending on how generously you squint. You lie there imagining the sun wrapped in a pastry of magnetic field and plasma, hurtling through the galaxy at 23 kilometers per second, its protective shell flexing and rippling in response to forces both internal and external. The shape of this shell determines how much galactic radiation reaches the planets inside it, including Earth. It determines the environment through which any future interstellar spacecraft would have to pass. And it remains, after all these decades and all this data, genuinely uncertain. The heliosphere is the house you live in, and nobody is quite sure what it looks like from the outside. You find that oddly comforting as your eyelids droop a little lower. Outside the heliosphere, the particle environment changes in ways that have implications not just for physics, but for survival. You lie still and let the numbers wash over you like a slow tide. Inside the heliosphere, the sun's magnetic field and solar wind act as a shield, deflecting and absorbing a significant fraction of the galactic cosmic rays that would otherwise rain down on the inner planets. These cosmic rays are not the gentle photons of starlight. They're atomic nuclei, mostly protons, but also heavier elements like helium, carbon and iron, accelerated to near the speed of light by supernova shock waves, active galactic nuclei, and other violent processes scattered across the universe. A single galactic cosmic ray particle can carry the kinetic energy of a baseball thrown at 60 miles per hour, compressed into something smaller than an atom. When these particles hit biological tissue, they shatter DNA strands, damage cell membranes, and trigger cascades of secondary radiation that multiply the harm. The heliosphere is, quite literally, the reason life on Earth is not perpetually bathed in a lethal rain of high-energy particles. Voyager's cosmic ray detectors have been tracking these particles for decades, and the data tells a clear story. Inside the heliosphere, the cosmic ray count fluctuates with the 11-year solar cycle. When the sun is active, its magnetic field is stronger and more turbulent, and it deflects more cosmic rays, pushing the count down. When the sun is quiet, the field weakens, and more cosmic rays leak through, nudging the count up. This modulation is well documented and has been studied from Earth orbit for years. But Voyager provides the view from the boundary itself, and the contrast is stark. As Voyager 1 approached the heliopause, the galactic cosmic ray count climbed steadily. When it crossed the boundary in August 2012, the count jumped sharply and then levelled off at a value roughly twice what had been measured inside the heliosheath. Voyager 2, crossing in 2018, recorded a similar jump. Outside the heliosphere, the cosmic ray flux is constant, unmodulated by the solar cycle, a steady rain of high-energy particles falling from every direction. The heliosphere, for all its messy and uncertain shape, cuts this radiation roughly in half. If you are planning a trip to another star, this is the kind of information that would keep you awake at night, which is ironic given the current purpose of your evening. A mainstream historical fact connecting cosmic rays to broader science is that these particles were first discovered in 1912 by Victor Hess, an Austrian physicist who carried electroscopes on balloon flights to high altitudes, and found that the ionization of air increased with height rather than decreasing as expected. The radiation was coming from above, not from the ground, and Hess correctly concluded that it originated in space. He received the Nobel Prize in Physics in 1936 for the discovery. More than a century later, Voyager is measuring the unfiltered version of the same radiation that Hess detected through Earth's protective atmosphere, directly and without the heliosphere's moderating influence. The energy spectrum of galactic cosmic rays outside the heliosphere also carries important information. Inside the heliosphere, the spectrum is distorted by the solar wind, which preferentially blocks lower energy particles, while allowing higher energy ones to pass through. This means that measurements taken near Earth always underestimate the true number of low-energy cosmic rays in the galaxy. Voyager, sitting outside the filter, measures the unmodified spectrum for the first time, and the result confirms theoretical predictions while refining the details. The low-energy end of the spectrum, below about 200 million electron volts per nucleon, is significantly higher than what is observed at Earth, revealing a population of relatively sluggish cosmic rays that the heliosphere normally hides from view. These low-energy particles are thought to be produced primarily by the shock waves of nearby supernova remnants, the expanding shells of debris left behind when massive stars explode. By measuring them directly, Voyager provides a new window into the recent history of stellar explosions in our galactic neighbourhood. Here is a quirky detail about cosmic rays that makes them even more interesting. Despite their name, cosmic rays are not rays at all. They are particles, individual atomic nuclei hurtling through space at enormous speeds. The misleading name dates to the early 20th century, when scientists assumed the radiation was electromagnetic in nature, similar to gamma rays. By the time it was established that cosmic rays are actually particles, the name had stuck and nobody could be bothered to change it. Science is full of names that are technically wrong but too entrenched to fix. Planetary nebulae have nothing to do with planets, shooting stars are not stars, and cosmic rays are not rays. You just have to accept these things and move on. The implications of Voyager's cosmic ray data extend to fields far beyond heliophysics. Astrobiologists care about the galactic radiation environment because it constrains where life can exist and how it might evolve. Planets without strong magnetic fields or thick atmospheres would be exposed to the full brunt of galactic cosmic radiation, and on worlds outside a stellar heliosphere, the exposure would be even worse. Engineers designing future interstellar spacecraft care because the radiation environment dictates shielding requirements. A crewed mission to another star would need to transit the interstellar medium for years or decades, fully exposed to the unfiltered cosmic ray flux that Voyager is now measuring. The data suggests that the shielding requirements would be substantial, far more than what current spacecraft designs provide. Scholars still argue about whether passive shielding, active magnetic deflection, or some combination of both would be the most practical approach. The debate is premature in some ways, since interstellar crewed travel remains a distant prospect, but Voyager's measurements ensure that when the conversation does become practical, it will be grounded in real data rather than guesswork. You feel the invisible rain of cosmic rays passing through your own body as you lie here, about 1 particle per square centimetre per second at Earth's surface, reduced to harmless background levels by the atmosphere and the magnetosphere above your head. Out where Voyager drifts, there is no atmosphere, no magnetosphere, no heliosphere. Just the raw flux of the galaxy, pouring in from every direction, steady and relentless, and older than the sun. It is not a comfortable thought, but it is a useful one, a reminder that the cocoon of safety surrounding your planet is not a given. It is a product of physics and proximity, and the particular star you happen to orbit. You close your eyes a little tighter and let the heliosphere hold you. The spacecraft are dying. Not dramatically, not all at once, but slowly and inevitably. the way a candle burns down or a battery drains in a flashlight left on overnight. You lie in the dark and feel the symmetry of that image, a machine running out of power in the deepest darkness any human object has ever known. The power source is plutonium-238, a radioactive isotope that generates heat through alpha decay, and that heat is converted into electricity by thermocouples in the 3 radioisotope thermoelectric generators bolted to each spacecraft. In 1977, each Voyager had about 470 watts of electrical power available. That number drops by roughly 4 watts every year as the plutonium decays and the thermocouples degrade. By the early 2020s, each spacecraft was running on less than 250 watts, barely enough to power a couple of old-fashioned incandescent light bulbs. Everything that Voyager has discovered about the edge of the solar system and beyond has been accomplished on an energy budget that would not keep your phone charged. The decline is relentless and mathematical, governed by plutonium-238's half-life of 87.7 years. This means that roughly half the original plutonium has decayed since launch, and the rest will continue to decay at the same exponential rate regardless of what anyone on Earth does. There is no way to refuel the generators, no way to replace the thermocouples, no way to send a repair crew to a spacecraft that is 18 billion kilometers away and moving at 17 kilometers per second. The mission team can only manage the decline, making careful decisions about which instruments to keep running and which to sacrifice. Those decisions have been agonizing. A mainstream historical fact about the Voyager power management is that the instrument shutdowns have been planned in stages, guided by a priority list that balances scientific value against power consumption. The cameras were the first to go, powered down permanently in 1990 after the pale blue dot photograph, partly to save power and partly because there was nothing left to photograph. The ultraviolet spectrometer was turned off. The infrared spectrometer was turned off. The photopolarimeter, which had been partially broken since Saturn anyway, was switched off. One by one, the instruments that had dazzled the world during the planetary encounters were put to sleep, each shut down a small funeral for a capability that would never return. By the 2020s, each spacecraft was running only a handful of instruments. Voyager 1 operates its magnetometer, its cosmic ray detector, its plasma wave instrument, and its low-energy charge particle detector. Voyager 2 runs the same suite plus its still-functioning plasma science instrument, that precious survivor from 1977 that has outlasted every expectation. Even these remaining instruments cannot all run simultaneously at full power. The mission team has had to reduce heating to the spacecraft's propellant lines and instrument platforms, allowing components to cool to temperatures far below their design specifications. Some parts of the spacecraft are now operating at -79 degrees Celsius, conditions that the original engineers never imagined and never tested for. The fact that the instruments continue to function at all is a testament to the conservative engineering philosophy of the 1970s, a build-it-tough approach that has proven its worth across 5 decades. Here's a quirky detail about the power management that reveals the ingenuity of the mission team. In 2019, engineers switched Voyager 2 to a backup power regulator that had not been used since 1981, freeing up a small amount of additional power for the science instruments. The backup had been sitting dormant for 38 years, untested and unmonitored, and nobody was entirely certain it would work. It did. In 2023, the team found another way to squeeze out power by tapping into a small reserve that had been set aside for a safety mechanism designed to protect the spacecraft in case of a voltage spike. The voltage spike had never occurred in 46 years, and the engineers calculated that the risk of repurposing that power for science was worth it, compared to the certainty of losing another instrument. These decisions are made by engineers who were not yet born when the spacecraft launched, working with documentation written by people who have long since retired, using tools and languages that predate the personal computer. It is like maintaining a medieval cathedral with the original blueprints, except the cathedral is moving at 60,000 kilometers per hour and the blueprints are in Fortran. The thermal situation is equally precarious. The spacecraft generate waste heat from their electronics and their power systems, and this heat has kept the internal components above their minimum operating temperatures for decades. But as the power drops, so does the waste heat, and the spacecraft are slowly freezing from the outside in. The propellant lines that feed the attitude control thrusters are of particular concern. If the hydrazine fuel freezes, the spacecraft lose the ability to orient their antennas toward Earth, and the mission effectively ends. Engineers have been turning off heaters one by one, diverting every possible watt to the science instruments, and trusting that the remaining heat from the electronics will be enough to keep the hydrazine liquid. So far, it has been, but the margin grows thinner every year. NASA's current estimates suggest that at least one science instrument on each spacecraft can be kept running until approximately 2025 to 2030, with complete power loss expected sometime in the mid-2030s. After that, the spacecraft will continue to coast through interstellar space, silent and inert, carrying their golden records and their dead instruments on a journey that has no destination and no end. The plutonium will continue to decay, growing cooler and quieter over centuries, and the thermocouples will eventually produce no electricity at all. The spacecraft will become artifacts, not of science, but of archaeology, the oldest and most distant relics of a civilization that built them in an era of vinyl records and rotary telephones. You think about that. The transition from living mission to eternal relic, and it feels less like an ending than a change of state. The discoveries do not stop being true when the instruments go dark. The data has already been sent home. The golden record does not need electricity to exist. Voyager will continue to carry humanity's message through interstellar space long after every person alive today has been forgotten, which is either the most hopeful or the most melancholy thought you've ever had while trying to fall asleep. You let it be both, and you drift a little deeper. The whisper that reaches Earth from Voyager 1 has been travelling for over 22 hours by the time it arrives. You let that sink in while you lie here in the warm dark. A signal moving at the speed of light, the fastest anything can travel in this universe, takes nearly an entire day to cross the distance between the spacecraft and the nearest radio dish on Earth. If you sent a message right now saying hello, and Voyager could somehow hear it and respond immediately, you would not receive the reply until nearly 2 days later. This is not a phone call, it is correspondence, the slowest and most extraordinary pen-pal relationship in human history. The transmitter aboard each Voyager operates at 23 watts. 23 watts. The light inside your refrigerator uses more power than that. A typical cell phone tower broadcasts at several hundred watts and reaches a few miles. Voyager's transmitter reaches over 15 billion miles, a feat that says less about the power of the signal and more about the sensitivity of the ears listening for it. By the time Voyager's radio signal reaches Earth, it is spread out over such an enormous volume of space that the power arriving at the antenna is roughly 20 billion times weaker than the power produced by a digital watch battery. Detecting this signal is like trying to hear a mosquito buzzing on the surface of the moon while standing in a noisy restaurant. And yet, 3 times a day, every day, a 70-meter radio dish somewhere on Earth swings toward the sky, locks onto that faint hum, and pulls data out of the noise. The network responsible for this miracle is called the Deep Space Network, and it is one of the most remarkable and least famous pieces of infrastructure on the planet. 3 facilities, spaced roughly 120 degrees apart around the globe, in Goldstone, California near Madrid, Spain, and near Canberra, Australia, ensure that at least one dish can see any point in the sky at any time. Each facility has multiple antennas, the largest of which are 70 meters in diameter, massive parabolic dishes that can be steered with millimeter precision to track a spacecraft moving through the sky at a rate determined by Earth's rotation and the spacecraft's own trajectory. The Deep Space Network does not serve Voyager alone. It communicates with every active deep space mission NASA operates, from Mars rovers to the New Horizons probe beyond Pluto. Scheduling antenna time is a constant juggling act, and Voyager, being far away and transmitting at a trickle, requires long blocks of dedicated listening time to collect meaningful amounts of data. A mainstream historical fact about the Deep Space Network is that it was established in 1963, originally to support the early Mariner missions to Venus and Mars. It has been in continuous operation for over 6 decades, evolving and upgrading as missions have pushed deeper into space. The 70-meter dishes at each site were originally 64 meters and were expanded in the 1980s, partly to support Voyager's encounters with Uranus and Neptune, where the signal was so faint that the existing dishes could not collect enough photons to reconstruct the images clearly. The expansion added roughly 50% more collecting area, which translated directly into the ability to receive data at a usable rate from distances that would otherwise have been beyond reach. Without that upgrade, the spectacular images of Uranus and Neptune systems might never have been captured. You owe those photographs to a few extra meters of aluminum mesh stretched across a dish in the Australian desert. The data rate from Voyager has dropped steadily over the decades as the spacecraft have moved farther away and as instruments have been turned off. During the Jupiter encounters, data flowed at rates up to 115 kilobits per second, fast enough to transmit a full image in about 48 seconds. At Uranus, the rate had dropped to roughly 30 kilobits per second. At Neptune, it was lower still. Today, Voyager 1 transmits at about 160 bits per second. To put that in context, loading a single modern web page at that rate would take several days. A single, high-resolution photograph from your phone would take weeks. The mission team receives small packets of instrument readings, magnetic field measurements, particle counts, plasma wave data, each one compressed and encoded and transmitted with a precision that leaves almost no room for error. Every bit is precious. Here's a quirky detail about how the signal is decoded that might impress you if you're still awake enough to appreciate it. Voyager uses a form of error-correcting code called a GOLAY code, augmented by a convolutional code, to protect its data against the inevitable noise of deep space communication. These codes add redundancy to the transmitted signal, allowing the ground receivers to detect and correct errors caused by interference, thermal noise, and the sheer weakness of the signal. The coding scheme was state-of-the-art in the 1970s and is now taught in introductory communications engineering courses as a historical example. Modern missions use more advanced codes, but Voyager's error correction still works reliably after nearly 5 decades, a testament to the mathematical elegance of the original design. Scholars in coding theory sometimes refer to the Voyager mission as one of the most successful real-world applications of channel coding, a case study in wringing every last drop of information from a signal that by all rights should be undetectable. The 70-meter dishes are aging themselves. The Goldstone facility's main antenna, known as DSS-14, was built in 1966 and has been upgraded multiple times but remains fundamentally a structure from the Johnson administration. NASA has been building new 34-meter dishes with more modern technology, using arrayed configurations to match or exceed the sensitivity of the older giants. But the transition is gradual, and the old dishes still carry a disproportionate share of the deep space communication burden. There is something poignant about the image of two aging machines, one in space and one on the ground, straining to hear each other across a distance that grows by about 1.5 million kilometers every day. You picture the scene: a desert night in Canberra, clear and cold, the Milky Way arching overhead in a way city dwellers never see. A 70-meter dish tilts slowly on its bearings, tracking an invisible point in the constellation Ophiuchus, where Voyager 1 happens to be. The receiver amplifies a signal so faint it is measured in fractions of a femtowatt. Computers strip away the noise, apply the error-correcting codes, and extract a stream of ones and zeros that, when reassembled, describe the magnetic field strength, the cosmic ray count, and the plasma wave frequency at a point in interstellar space 18 billion kilometers away. The whole process takes hours. The data that arrives could fit on a floppy disk, and yet it is the most distant conversation in the history of language, a dialogue between a species and its farthest emissary, conducted at the speed of light across a gulf that human intuition was never designed to comprehend. In the spring of 2022, something goes wrong with Voyager 1, and for a while nobody can figure out what it is. You lie in the dark and imagine the scene at JPL, a room full of engineers staring at screens displaying data that has become, quite suddenly, nonsensical. The spacecraft's attitude, articulation and control system, the subsystem responsible for keeping Voyager 1 oriented correctly in space, begins sending back telemetry that does not match reality. The antenna is still pointed at Earth. The signal is still arriving. The science instruments are still collecting data. But the housekeeping telemetry, the internal status reports that tell engineers what the spacecraft thinks it is doing, has turned to gibberish. The numbers describe impossible orientations and non-existent maneuvers. Voyager 1, after 45 years of near-flawless operation, appears to be hallucinating. The problem is maddening because the spacecraft is otherwise functioning normally. If the attitude control system were truly malfunctioning, the antenna would drift off target and the signal would fade. But the signal is steady. Voyager 1 is holding its position perfectly. It just cannot accurately describe what it is doing, like a person who can walk in a straight line but cannot explain how their legs work. The disconnect between performance and reporting suggests a problem not in the control system itself, but in the computer that processes and formats the telemetry data before transmitting it home. Voyager 1 has 3 onboard computers, each dedicated to a different function. The flight data subsystem handles science data formatting. The computer command subsystem manages commands from Earth. And the attitude and articulation control subsystem computer manages orientation and antenna pointing. It is this third computer that is producing the corrupt telemetry. The engineers suspect a hardware failure, specifically a problem with the computer's memory. But diagnosing the issue from 18 billion kilometers away using a communication link with a 44-hour round-trip delay is not exactly straightforward. Every diagnostic command must be carefully composed, transmitted, and then waited upon for nearly 2 days before the response arrives. A troubleshooting session that might take an afternoon in a terrestrial lab stretches across weeks and months in deep space. A mainstream historical fact about Voyager's computers is that they were designed and built using technology from the early 1970s. Each computer contains about 69 kilobytes of memory, implemented in plated wire technology, a type of non-volatile storage that predates modern semiconductor memory. Plated wire memory stores information as magnetic patterns on tiny wires woven into a grid and it was chosen for Voyager because of its radiation tolerance and ability to retain data without power. The technology is so old that the engineers troubleshooting the 2022 anomaly had to consult documentation written decades before many of them were born, some of it stored only in paper form in filing cabinets and archived boxes at JPL. Imagine debugging a computer built before the invention of the personal computer, using manuals that smell like old libraries, while the computer in question is farther away than any object you can see in the night sky. By late 2022, the engineering team had narrowed the problem to a specific section of memory in the attitude control computer. A block of memory had failed, probably due to a single damaged chip, and the computer was attempting to route telemetry data through this corrupted section, producing the garbled output. The solution was conceptually simple, but operationally terrifying. The team needed to remap the computer's memory allocation, telling it to avoid the damaged section and store the relevant data elsewhere. This required uploading a software patch to a 45-year-old computer, running on plated wire memory across a communication link with a 22-hour one-way light delay. If the patch contained an error, or if it was corrupted during transmission, or if it caused an unexpected interaction with the ancient software, the consequences could range from a minor inconvenience to a permanent loss of contact with the spacecraft. Here is a quirky detail about the patch process that reveals the extraordinary caution of the mission team. Before uploading anything to Voyager 1, the engineers tested the patch on a ground-based simulator, a replica of Voyager's computer systems maintained at JPL specifically for this purpose. The simulator is built from spare parts and documentation dating to the 1970s, a kind of living museum of obsolete technology kept operational for exactly this kind of emergency. The team ran the patch through the simulator hundreds of times, checking for conflicts, timing errors, and unexpected behaviours before transmitting it to the real spacecraft. Even then, they uploaded only a portion of the fix first, waited for the response, verified it worked, and then sent the rest. The entire process took months. Patience in deep space engineering is not a virtue. It is a survival strategy. The patch worked. In April 2023, Voyager 1 began returning coherent telemetry for the first time in months, and by late 2023 the engineering data was fully restored. The science instruments, which had continued operating normally throughout the anomaly, resumed sending data through the repaired formatting pipeline. The engineers who executed the fix received quiet congratulations from the planetary science community, the kind of understated recognition that is typical of a field where the most heroic acts involve typing commands into a terminal and then waiting a very long time. But the 2022 anomaly was not the first glitch, and it will not be the last. Both Voyagers have experienced numerous hardware failures and software anomalies over the decades. Voyager 2 once spent several weeks in 2010 sending data in a format that could not be decoded, the result of a single flipped bit in the flight data subsystem memory. A command was sent to reset the affected memory register, and normal operations resumed. In 2020, Voyager 2 unexpectedly shut down all 5 of its remaining science instruments after a power management routine drew too much current from the degraded electrical system. The instruments were restarted one by one over the following weeks. Each anomaly is a reminder that these spacecraft are operating far beyond their design lifetimes, in conditions their builders never anticipated, maintained by a relay of human engineers who pass the knowledge from one generation to the next like a sacred text. Scholars still argue about how long meaningful communication with the Voyagers can be maintained. The optimists point to the ingenuity of the engineering team and the remarkable durability of the hardware. The pessimists point to the relentless decline of the power supply and the increasing fragility of components that have been exposed to cosmic radiation and thermal cycling for half a century. The truth, as usual, lies in the uncomfortable middle. Each spacecraft will continue to function until it does not, and the exact moment of final failure is unpredictable. You might wake up one morning to the news that Voyager has gone silent, or it might outlast every prediction and keep whispering into the 2030s. The uncertainty is part of the story, a reminder that all communication eventually ends, and the only question is how much you manage to say before it does. There is so much that Voyager cannot tell us. You lie here in the quiet and feel the edges of what is known dissolving into what is merely guessed at, like the boundary between wakefulness and sleep that you yourself are drifting along right now. The spacecraft have been extraordinary witnesses, but they are also profoundly limited. Two small machines with 1970s instruments crossing a tiny sliver of a boundary that extends in every direction for billions of kilometers. What they have measured is invaluable. What they have missed is vast. Start with the Oort cloud, that hypothetical shell of icy bodies believed to surround the solar system at distances of 2,000 to 100,000 astronomical units from the Sun. The Oort cloud is thought to be the source of long-period comets, those ghostly visitors that drop into the inner solar system on orbits so elongated they take thousands or millions of years to complete. Gravitational nudges from passing stars, from the galactic tide, from giant molecular clouds drifting through the Milky Way, occasionally dislodge an Oort cloud object and send it tumbling sunward, where it develops a tail and briefly becomes visible before swinging back out into the dark. The cloud is named after Jan Oort, the Dutch astronomer who proposed its existence in 1950, and it remains entirely unobserved. No telescope has ever imaged an Oort cloud object in situ. No spacecraft has ever passed through it. Its existence is inferred entirely from the orbits of comets that have visited the inner solar system, which is a bit like deducing the existence of an ocean by studying the fish that occasionally wash up on your beach. Voyager 1, despite being the most distant human-made object, is nowhere near the Oort cloud. At roughly 165 astronomical units from the Sun, as of the mid-2020s, it has covered less than 1% of the distance to the cloud's inner edge. At its current speed, Voyager 1 will not reach the inner Oort cloud for another 300 years and will not exit the outer edge for roughly 30,000 years. By that time, the spacecraft will have been silent for millennia, its plutonium fully decayed, its instruments long dead, its golden record riding in perpetual darkness aboard a frozen shell of aluminum and titanium. It will pass through the Oort cloud without knowing it, which is both anticlimactic and somehow fitting for a cloud that has never been directly observed by anyone. Then there is the question of the bow shock, or rather, the question of whether the bow shock exists at all. As the Sun moves through the interstellar medium, you might expect it to create a shockwave in front of it, similar to the shockwave created by a supersonic aircraft. This hypothetical feature, called the bow shock, was predicted by early heliospheric models and appeared in textbook diagrams for decades. But data from the Interstellar Boundary Explorer satellite and revised estimates of the Sun's speed through the interstellar medium suggest that the Sun may be moving too slowly relative to the surrounding gas to create a true shock. Instead, there may be only a gentler feature called a bow wave, a gradual compression rather than a sharp discontinuity. Scholars still argue about this, and the distinction matters because a bow shock and a bow wave create very different upstream conditions that would affect the heliosphere's shape and the environment through which any outward-bound spacecraft must travel. Voyager's instruments cannot settle the question because both spacecraft crossed the heliopause roughly in the direction of the Sun's motion, not far enough ahead to reach whatever structure exists upstream. A mainstream historical fact that connects to these unknowns is the story of Pioneer 10 and Pioneer 11, the two spacecraft that preceded Voyager into the outer solar system. Both pioneers crossed the orbits of the outer planets in the 1970s and headed toward interstellar space on trajectories different from the Voyagers. Contact with Pioneer 11 was lost in 1995 and with Pioneer 10 in 2003, both due to power depletion and antenna misalignment. Neither spacecraft reached the heliopause before going silent. If they had survived, they would have provided additional crossing points in different directions, helping to constrain the heliosphere's shape and the nature of the boundary in regions that Voyager never sampled. Their silence is a loss that cannot be recovered. Here is a quirky detail about the unknowns that makes them even more tantalizing. Some theoretical models predict that the interstellar medium near the Sun contains structures called local fluff and local bubble that are remnants of ancient supernova explosions. The local bubble is a region of hot, low-density gas roughly 300 light-years across that the Sun has been travelling through for several million years. Within this bubble, the Sun is currently passing through a smaller, denser cloud of warm gas called the local interstellar cloud, or local fluff, which is the medium that Voyager is directly sampling. Some astronomers believe the Sun may be near the edge of the local fluff, about to emerge into an even less dense region of the local bubble, which would change the pressure on the heliosphere and potentially alter its size and shape. Voyager's measurements of the interstellar medium's density and temperature are our only in situ data points for these structures, but 2 data points in a region that spans light years are not enough to determine where the boundaries lie or how they will shift. And then there are the truly speculative questions, the ones that sit at the boundary between mainstream science and the kind of late-night wondering that happens in exactly the sort of state you're in right now. Could Voyager's trajectory through interstellar space reveal anything about dark matter? Probably not directly, since dark matter interacts only gravitationally, and Voyager's instruments are designed to detect electromagnetic and particle phenomena. But some researchers have used Voyager's precise trajectory data to place very loose constraints on the density of dark matter in the solar neighbourhood, on the grounds that any significant concentration of invisible mass would slightly alter the spacecraft's path. The constraints are not competitive with other methods, but the attempt is a reminder that even a small, aging spacecraft can contribute to questions far larger than its original mission. Future missions have been proposed to do what Voyager cannot. The interstellar probe concept studied by NASA and the Johns Hopkins Applied Physics Laboratory envisions a dedicated spacecraft designed to reach the heliopause in 15 years rather than 35, carrying modern instruments capable of measuring the interstellar medium with precision that Voyager's 1970s technology cannot approach. The probe would also carry cameras capable of imaging the heliosphere from the outside, providing the first external photograph of our Sun's protective bubble. Scholars still argue about the optimal trajectory, the instrument suite, and the propulsion technology, but the scientific case is strong. Voyager showed us the door. A future probe could map the entire house. You feel the weight of all those unknowns pressing softly against your thoughts, not heavy but present, like the knowledge that there are rooms in your house you've never entered. The Oort cloud drifts in the dark. The bow wave shimmers or does not. The local fluff thins toward an edge no one has measured. And Voyager pushes on. Instruments fading, power dropping, carrying what it knows into a silence that will last longer than any civilization. The spacecraft will outlast us all. You lie here and let that thought arrive gently, not as something frightening, but as something quietly astonishing. A fact so large it wraps all the way around from overwhelming to peaceful. When the last instrument goes dark and the last watt of electricity flickers out sometime in the early 2030s, Voyager 1 and Voyager 2 will not stop moving. They cannot stop. There is nothing out here to slow them down. No atmosphere, no friction, no resistance of any kind. Newton's first law, the simplest and most elegant statement in physics, guarantees that an object in motion stays in motion unless acted upon by an external force, and in the void between stars, external forces are vanishingly rare. The spacecraft will coast at their current speeds, roughly 17 kilometers per second for Voyager 1 and 15 kilometers per second for Voyager 2, for millions of years, drifting through the galaxy like bottles dropped into an ocean with no shore. Voyager 1 is heading in the general direction of the constellation Ophiuchus, though the stars themselves will have moved considerably by the time the spacecraft gets anywhere near them. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of Gliese 445, a dim red dwarf star in the constellation Camelopardalis that is currently moving toward the Sun at a brisk clip. It will not enter the star's planetary system if one exists. It will simply drift past at interstellar distances, unnoticed and undetected, a tiny mote of aluminum and silicon and gold passing through the gravitational neighbourhood of a star that has no reason to care. Voyager 2, heading in a different direction toward the constellation Sagittarius, will pass within about 1.7 light-years of Ross 248, another red dwarf, in roughly 40,000 years as well. Neither encounter will be close enough for the star's gravity to significantly alter the spacecraft's trajectory. They will simply keep going. A mainstream historical fact that puts this timescale into perspective is the age of human civilization itself. The earliest known cities in Mesopotamia are roughly 6,000 years old. The oldest cave paintings are perhaps 40,000 years, comparable to the time it will take Voyager to reach the neighbourhood of another star. In 40,000 years, every language currently spoken on Earth will have changed beyond recognition or vanished entirely. Every building will have crumbled. Every nation, every institution, every cultural memory that exists today will have been replaced by things we cannot imagine. And Voyager will still be drifting, unchanged, carrying its golden record through a darkness that does not erode or forget. The golden record is designed to last. The copper disc, plated in gold and sealed inside an aluminum jacket with an electroplated uranium-238 sample whose decay rate serves as a clock, was engineered to survive in interstellar space for at least 1 billion years. The vacuum and cold of the interstellar medium are paradoxically excellent conditions for preservation. There is no oxygen to cause corrosion, no water to degrade the materials, no microbes to break down the organic compounds in the record's grooves. The primary threats are cosmic ray bombardment, which will slowly damage the record's surface over millions of years, and micrometeorite impacts, which could pit or crack the disk. But the rate of both processes is so low in the sparse interstellar medium that the record is expected to remain playable, at least in principle, for a time span that dwarfs the entire history of life on Earth. Here is a quirky detail about the golden record's longevity that borders on the philosophical. The record's intended audience is an extraterrestrial civilization, advanced enough to find the spacecraft, recognize it as artificial, decode the pictographic instructions on the cover, build a device to play the record and interpret the sounds and images encoded on it. The probability of this happening is, by any reasonable estimate, astronomically small. The galaxy is vast, the spacecraft are tiny, and even if intelligent civilizations exist elsewhere, the chances of one intercepting an object the size of a compact car drifting through interstellar space are roughly comparable to the chances of finding a specific grain of sand on a specific beach by randomly scooping up a handful. Carl Sagan understood this. The record was never really about communicating with aliens. It was about communicating with ourselves, about declaring to the universe that we existed, that we made music and fell in love and looked up at the stars and wondered. The record is a message in a bottle that may never be found, and its value lies entirely in the act of sending it. Scholars still argue about what should have been included on the record and what should have been left off. The committee that curated the contents faced impossible choices about how to represent the entirety of human culture in 90 minutes of audio and 116 images. Some critics have noted that the selection skews heavily toward Western classical music and underrepresents the musical traditions of Africa, Asia, and indigenous cultures worldwide. Others have pointed out that the greetings in 55 languages, while impressively diverse, include no representation of sign languages or non-verbal communication. The committee itself acknowledged these limitations, and Sagan later wrote that any attempt to summarize humanity on a single disc is inherently incomplete. The record is not a perfect portrait. It is a love letter, hastily written and imperfectly addressed, slipped into the pocket of a traveller who may never arrive. You let your breathing slow to match the pace of the spacecraft, steady and unhurried, moving through a darkness that holds no deadlines. The golden record carries the sound of a human heartbeat, recorded from the chest of a young woman who was quietly falling in love in a studio in New York City in 1977. That heartbeat will continue to exist, pressed into copper grooves and shielded by gold plating, long after every heart currently beating on Earth has stopped. It will drift past stars that have not yet been born. It will cross regions of the galaxy that no human eye has ever observed. And if the universe is kind, or merely patient, something might someday find it. Lower a stylus into the groove, and hear the sound of what it meant to be alive on a small blue planet, orbiting an ordinary star in an unremarkable arm of a spiral galaxy, a long, long time ago. The heliosphere is far behind now. The sun is just a star, bright but not special, fading with each passing year into the general glow of the Milky Way. The spacecraft do not know they are alone. They do not know they are drifting. They simply are the way a stone at the bottom of a river simply is, present and enduring and unaware of time. And you, lying here in your warm bed, are connected to them by a thread of radio waves that will soon break, and by a thread of imagination that will not. So let your eyes close all the way now. Let the hum of interstellar plasma fade to a whisper, and let the whisper fade to silence. The journey is not over. It will never be over. But you have followed it far enough for tonight, farther than almost anyone goes, out past the planets and through the heliosheath, and across the heliopause into the space between the stars. The universe is vast and cold and magnificent, and you are part of it. The same atoms, the same physics, the same ancient starlight that Voyager is sailing through right now. You're not separate from the darkness. You're the darkness looking back at itself, wondering, and that is enough. That is more than enough. Let the spacecraft carry the rest. You have earned your sleep. The fan hums softly. The room is warm. Somewhere 18 billion kilometers away, a 23-watt transmitter whispers a lullaby made of numbers, and a 70-meter dish in the desert leans in close to listen. The data will still be there in the morning. The stars will still be there. And Voyager, faithful and tireless and impossibly far from home, will still be drifting, carrying whale songs and Beethoven and the sound of a human heartbeat into the longest night there is.